Every star you've ever wished on is a decoy. Behind each pinprick of light lies an ocean of galaxies so vast that countless isn't even close. And in that ocean, the universe left fingerprints, hidden structures that map where we came from and where everything is going. So who built these cosmic cities? What forces sculpted them from the first light to today? And what do they reveal about our fate in the dark between galaxies? Tonight, the sky is not scenery. It is evidence, arriving late and bearing the weight of deep time. Follow that evidence far enough, and the universe begins to confess its methods. Light does not simply show us what is out there. It tells us when it happened and what changed along the way. In this film, distance becomes a chronology, and every spectrum becomes a ledger of temperature, motion, and chemical memory. We will read the faintest photons like forensic traces, measuring redshift, mapping dust-hidden regions, and letting radio and infrared reveal what visible light cannot. Yet the galaxies themselves are only the illuminated surface of a deeper architecture, an arrangement that seems to obey rules we can test, while refusing to explain why those rules exist. Somewhere between the first fragile structures and the grand spirals we know, a quiet majority took control. It does not shine, it does not cool, and it rarely collides. Yet it shapes where galaxies can gather, how they can grow, and what they can become. And at the centres of many galaxies, another influence waits in darkness, patient and precise. An engine that can build, regulate, or erase whole eras of star-making. We will move through environments that remake galaxies without touching a single star, and through encounters that leave tidal signatures stretching farther than imagination can comfortably hold. As the journey widens, the map itself changes, because the universe is expanding, and expansion sets boundaries that no spacecraft can negotiate. This is not a catalogue, and it is not a simple tour. It is an investigation into formation, transformation, and the unseen structures that decide what is possible. By decoding the light of galaxies across cosmic history, we approach an unsettling clarity about our origins, and an equally unsettling limit to what any observer can reach. A journey to all galaxies in our universe begins where the sky is closest, then pulls away until even far becomes a kind of past. What we find will be coherent in pattern, relentless in scale, and still, at its deepest causes, unresolved. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We start with a map that has no edge, then use our galactic neighbourhood as a key to read the wider cosmos. From the cosmic web to the first turbulent galaxies, we follow the clues toward the deepest fields and the horizon that closes behind them. Night feels close. It hangs above rooftops and trees, a familiar ceiling of scattered points that seem pinned in place. The air cools, insects fade, and the stars sharpen, each one a tiny signal slipping through our atmosphere. But the sky is not a ceiling. It is a record of travel time, written in light that has been moving long before we looked up. Every photon arriving now has already crossed distance, and distance in space becomes distance in history. Light does not deliver the present. It delivers a delayed message, and the delay is measurable with clocks and spectra. When you learn to read that delay, the night sky stops being decoration and becomes evidence. We start where our senses insist we belong. Earth is a small world with a thin atmosphere, a skin of gas only a few tens of kilometers thick. The blue we see is sunlight scattered by molecules, and the darkness above is not emptiness. It is simply the point where air stops glowing and the universe begins. Light leaves the ground, crosses a few kilometers, and we call it far because our bodies are built for short distances. A mountain ridge feels distant, and a city's glow looks like a horizon. Yet even that familiar glow is physics in motion. Photons bouncing, scattering, and leaking upward into space. Then we widen the frame. The moon is about a second away at light speed, close enough that a laser pulse can touch it and return in a heartbeat. Astronaut footprints are still there, but what matters here is the timing. Even our nearest neighbour is already a lesson in lag. The sun is 8 light minutes away, close enough to feel immediate and constant, yet never truly instantaneous. When the sun's light reaches your face, it left the solar surface minutes earlier. In that small gap is a quiet reminder that now is local, and the universe does not share it. The outer planets sit hours away in light travel time, still inside one star's neighborhood, still inside one gravitational family. A radio command to a distant probe is not a conversation. It is a call and wait ritual, paced by the finite speed of light. Beyond them, the solar system fades into a sparse halo of comets and cold debris. The Kuiper Belt and the distant Oort cloud are not bright rings in the sky. They are a diffuse reservoir of ice and rock, stirred by passing stars and the galaxy's tide. Even here, the first scale shift arrives. Our map stops being about places and becomes about time, because the only practical ruler is light itself. The universe forces us to measure with delays, and to accept that every direction is also a direction into the past. The nearest stars are years away. Their light began its trip before our current headlines, before our latest arguments, before today's weather. Proxima Centauri's photons cross interstellar space for more than 4 years, sliding through a thin mist of gas and magnetic fields. 100 light-years reaches back through recent human generations, still within a local bubble of hot, low-density gas. That bubble is not poetic language. It is a real cavity carved by ancient supernovae, and it shapes the interstellar medium around the Sun. 1,000 light-years begins to sample the Milky Way's disk, its dust lanes, and its spiral structure. Dust is not smoke. It is microscopic grains of carbon and silicates, efficient at blocking visible light while quietly re-radiating energy in infrared. At 10,000 light-years, we are no longer touring. We are measuring a galaxy from inside, trying to infer a whole structure while trapped in one of its rooms. The view becomes crowded, and the sky's brightness turns into a kind of fog made of unresolved stars. The Milky Way is roughly 100,000 light-years across. That number is not a metaphor. It is the time light needs to cross our home, and it is also a clue to how slowly galaxies change on human scales. We live embedded in its rotating disk, orbiting a center we cannot see directly, carried along at hundreds of kilometers per second. Our motion is smooth enough to feel still, yet precise enough to be measured through stellar velocities and Doppler shifts. Between us and that center, dust blocks visible light and hides much of the core. If our eyes were tuned to infrared, the Milky Way would look less like a thin band and more like a luminous, crowded city. So even our own galaxy teaches the first rule: what you see depends on wavelength. A galaxy is not just a bright patch. It is a gravitationally bound system, held together by mass and motion rather than by appearance. It holds stars, gas, and dust, and those components cycle. Gas collapses into stars, stars forge heavier elements, and winds return enriched material to space. It also holds dark matter that outweighs the luminous parts. We do not see it shining, and we do not catch it absorbing light, but its gravity organizes everything else. Without it, many galaxies would not remain intact and clusters would fly apart. Galaxies range from dwarfs, with about 10 million solar masses, to giants near 1 trillion, and their diversity is not cosmetic. Mass sets the depth of the gravitational well, which sets how strongly gas is retained and how easily star formation can be quenched. Their sizes span from small diffuse spheroids to vast disks with extended halos. Some are so faint that they are almost made of darkness, visible only by the few stars they manage to keep. Others blaze with billions of suns and still hide most of their mass in invisible form. Their shapes are not fixed categories. They are outcomes of gravity, rotation and collisions, and they can change with time. A graceful spiral can be disturbed, heated and reshaped by encounters, leaving behind a smoother, rounder remnant. From inside the Milky Way, we infer structure by motion and by radiation. We track stellar orbits, gas clouds, and the pull of mass we cannot see, building a model from partial views. We also listen to the Galaxian radio, where hydrogen broadcasts at a precise wavelength. We measure how fast stars move at different radii, and the curves refuse to fall the way simple gravity from visible matter predicts. That mismatch is a clue, and it is stubborn. Most of the galaxy's mass is missing from our direct view, yet it announces itself through dynamics. This problem is not new. In the early 20th century, astronomers began to suspect unseen mass in clusters, and later, the flat rotation curves of spiral galaxies made the case unavoidable. The language changed over time, but the observation remained. light does not trace all matter. Now the map expands again. The Milky Way is one galaxy among many, and the word many grows quickly once you step beyond our disk. On clear nights, the unaided eye sees only a fraction of what is there, because distance and faintness hide almost everything. Its nearest large companion is Andromeda, more than 2 million light-years away. That distance means we see Andromeda as it was before modern humans existed, when early ancestors were still learning fire and stone. In images, its disk tilts toward us like a pale blade, dust lanes etched across its glow. The Triangulum galaxy joins them, smaller and more delicate, with star-forming regions that sparkle in ultraviolet and infrared. Smaller dwarfs swarm around like satellites, some stretched by tides, some barely holding together. Together they form the local group, a modest island of matter in a larger sea. Even within this small neighbourhood, gravity is already shaping the future. Andromeda and the Milky Way are moving toward each other, not because space is shrinking, but because local gravity can overcome expansion here. The collision is far away in time, yet it reminds us that galaxies are not permanent arrangements. Step farther out, and the islands connect. Groups gather into clusters, and clusters can contain hundreds or thousands of galaxies bound in a common halo. In cluster images, you see smooth yellow ellipticals, faint smudges at the edge of detection, and arcs of distorted light made by gravity. Clusters thread into filaments. Voids open between them like dark basins, regions where matter is sparse and galaxies are rare. This is the cosmic web, a pattern shaped by gravity acting on early fluctuations, amplified over billions of years. It is not a decorative structure. It is the scaffolding that guided galaxy formation, channeling gas along filaments and feeding growth at their intersections. When simulations render it, the web looks like frost spreading on glass, branching, connecting, and leaving emptier patches behind. At the largest scale we can observe, the universe has a horizon. It is not a wall in space, it is the limit set by light travel time, because the universe has an age and light has a speed. The observable universe is about 93 billion light-years across in today's distance measure. That number includes expansion, which means the space between us and distant sources stretched while the light was in flight. A photon can travel for 13.8 billion years and still come from a place now much farther away. So our map has no edge in principle, yet it has an edge in practice. We cannot see beyond what light has had time to reach us since the beginning, and we cannot receive messages from regions forever outside our horizon. The boundary is not drawn on space, but on causality. This film asks a question that sounds like a travel plan. How do we journey to all galaxies in our universe when even nearby stars are out of reach? The honest answer is that we cannot visit them, not with ships or lifetimes, and not with any propulsion we can plausibly build. Even crossing the Milky Way would take longer than civilization has existed, even at speeds that would feel miraculous today. Yet the scientific voyage is real. We travel by reading light as evidence, and we accept that the journey is interpretive rather than physical. We let photons be our messengers, and we reconstruct a history we never witnessed. We treat the sky like a laboratory notebook, where each spectrum is a measurement and each image is a data table. The romance is not in pretending we are there. It is in realizing we can still know. To do that, we must define what it means to observe a galaxy. Visible light shows starlight and the shapes our eyes evolved to notice, but it also biases us toward what is unobscured. Invisible images, spiral arms look like brushstrokes, and bright star clusters pop like sparks. Infrared reveals stars behind dust and the glow of warm grains heated by formation. In infrared maps, dusty lanes become translucent, and hidden nurseries appear as soft reddish embers. The same galaxy can look calmer or more violent depending on which wavelengths you choose. Radio waves trace cold gas. The 21 centimeter line maps neutral hydrogen across disks and halos because a subtle flip in hydrogen's electron and proton alignment emits a photon at a precise frequency. It is faint, but it is reliable, and it outlines the raw fuel for future stars. X-rays expose hot plasma in clusters and the violent environments near compact objects. In X-ray images, clusters glow like ghostly clouds, revealing gas heated to tens of millions of degrees by gravity and shocks. These are places where matter is so energetic that atoms are stripped and light is born from collisions. Gamma rays mark extreme particle acceleration, often linked to jets and explosive remnants. They hint at magnetic fields twisted into tight coils, and at particles pushed close to light speed. In that regime, the universe is not just luminous. It is actively transforming energy into radiation. No single band tells the whole story. Each one is a different census of matter and energy, and each one comes with its own blind spots. When we combine them, we do not just add pictures, we cross-check reality. Multi-wavelength astronomy is not optional. It is the only way to avoid being fooled, because nature hides processes behind dust, temperature, and scale. A galaxy can look quiet in visible light while raging in infrared, where star formation is buried inside thick molecular clouds. Dust can erase a galaxy's visible brightness while leaving its infrared output strong. A black hole can be nearly invisible in starlight and dominate in X-rays, where hot gas spirals inward and radiates before it disappears. Cold gas can be abundant without shining much at all except in radio lines. So the universe hides its workings in plain sight, spread across the spectrum. The trick is to learn which light is diagnostic and which light is merely pretty. Observation becomes translation, and translation requires more than one language. The next tool is more abstract. It is redshift, written as Z, and it is one of the most powerful ideas in astronomy. Redshift is the universe's timestamp on light, because it encodes how much the cosmos expanded while the photon travelled. As space expands, wavelengths stretch, spectral lines slide toward the red, and the shift is measurable with exquisite precision. A pattern of atomic fingerprints, hydrogen, oxygen, iron, moves as a whole, and that coherent motion is what makes the measurement trustworthy. Redshift converts that pattern into a cosmic distance scale, although the conversion depends on cosmology and on how expansion has changed over time. At low redshift, recession speed is roughly proportional to distance, and the relation is simple enough to teach in one line. This is the Hubble, Lemaitre law. V is approximately H0 times d when z is small, and it was built from painstaking observations of galaxies and variable stars. Historically, it also corrected our sense of scale, because it revealed that nebulae were not clouds inside the Milky Way. They were other galaxies entirely. It is not galaxies moving through space like shrapnel. It is space itself expanding between us, carrying galaxies along while local gravity keeps bound systems intact. That distinction matters because it tells us the expansion is not an explosion into emptiness. It is a stretching of the metric that defines distance. Redshift does more than locate a galaxy. It places it in an era, and it tells us what kind of universe that galaxy inhabited. A higher Z means the light left earlier, when the universe was younger and denser, and when galaxies were still assembling their basic forms. So when we point a telescope outward, we are also pointing backward in time. The deep skies are layered archives stacked by distance and delay. Nearby galaxies are recent chapters, written in stable orbits and mature stellar populations. Distant galaxies are early drafts, written before disks settled and bulges matured, and often revised by collisions. Their light can be faint and stretched into infrared, and their shapes can look like fragments rather than finished systems. We are not just seeing far, we are seeing young. Here the narrative tension sharpens. Our senses are tuned to the local and the stable, to objects that do not change while we watch. But the universe is neither. It evolves, and its early forms are unfamiliar, because the conditions were different and the clock was running fast. Look far enough, and galaxies stop looking like galaxies. They become clumpy, chaotic and irregular, lit by bursts of newborn stars that burn hot and blue. Some are assembling from fragments, and some are colliding and reshaping in real time, their gas compressed into bright knots. The farther we look, the more we witness formation rather than completion. We see turbulence, feedback and rapid growth, and we have to ask what normal even means. Are today's spirals the rule, or are they the calm after an ancient storm? This is why the title matters. The map that has no edge is not a contradiction. It is a statement about method and about humility, because it admits that our reach is limited but our inference can be global. We cannot reach every place, but we can sample every epoch. We can build a map from light that arrives here, even when the sources are unreachable, and we can do it with statistics as well as with portraits. We can count galaxies, trace their clustering, and infer the invisible framework that shaped them. The journey is not a line through space. It is a descent through time, guided by photons that have been travelling since long before Earth had oceans. Each observation is a meeting with an earlier universe, and each earlier universe has its own rules of appearance. Still, the map is incomplete. Two absences haunt every measurement, and they are not minor accounting errors. One is missing mass. Dark matter shapes rotation curves and holds clusters together, and it also deepens the wells where gas can cool and form stars. It does not emit or absorb light in the usual ways, yet its gravity is decisive. We detect it through its pull, through the motions it enforces, and through the way it bends light from background galaxies, an effect that turns mass into a lens. The other is missing light. Dust obscures star formation and hides whole populations, especially in the most active gas-rich systems. Even the brightest surveys can undercount what is faint, distant, or reddened, because the universe is not obligated to be convenient. So our story begins with a warning. Most of what drives galaxies is invisible, and much of what is visible is incomplete. The cosmos is generous with photons, yet stingy with clarity. We will return to this motif again and again. Dark matter sets the scaffolding of the cosmic web, and galaxies grow along its filaments, fed by flows of gas that are difficult to see directly. Obscured star formation changes how we measure growth, and it reshapes the cosmic energy budget by moving light from visible into infrared. Black holes add another hidden engine, converting infall into radiation and jets that can heat or expel gas. Their influence can extend far beyond their tiny size because energy couples to surrounding matter. Each of these forces leaves signatures in spectra, motions, and background glow. The structure of the quest must match the structure of the universe. Each chapter will be a region, not only in space but in physical conditions, because galaxies are shaped by environment as much as by internal physics. We begin with nearby galaxies, where individual stars and gas clouds can be resolved, and where uncertainties can be confronted. We move to the cosmic web, where environment and clustering control growth, and where the large-scale pattern becomes a kind of boundary condition. We enter the era of early galaxies, where the first heavy elements appear and spread, seeding future planets and future chemistry. We follow collisions and mergers, where gravity rearranges disks into spheroids and triggers bursts of star formation. We confront black holes, where compact mass influences galaxies far beyond its size, and where accretion can outshine billions of stars. We track dark matter, where the dominant mass is inferred through lensing and motion, and where the map is drawn by gravity alone. We end with the cosmic future, where expansion and exhaustion set the long horizon, and where the night sky itself will change as distant galaxies slip beyond visibility. The questions become quieter there, but no less profound. What remains observable when the universe keeps stretching? But first, we must ground the voyage in something we can test. The Milky Way is our laboratory, yet it is also our blind spot, because we are inside it and cannot see it as a whole. We cannot step outside it, so we use neighbours as mirrors, comparing what we infer with what we can view directly. In nearby galaxies, we can compare models to details, and we can calibrate our tools against resolved structures. We can measure distances by standard candles, map gas by radio lines, and weigh halos by dynamics, checking one method against another. Then we can carry those methods into the deep field, where galaxies are faint and time is raw. So the opening move is simple. We stand on Earth and admit our limits, and we turn those limits into a disciplined approach. We accept that travel is replaced by observation, and observation is replaced by inference, because the universe is too large for anything else. We let light be the vehicle, we let redshift be the odometer, we let the cosmic web be the road, built from matter we cannot see, yet traced by the galaxies that formed along it. The night sky becomes a doorway again, not into fantasy, but into deep time. Every galaxy is a different distance, and therefore a different age, and the sky becomes a mosaic of epochs. To journey to all galaxies is to read the universe's autobiography, page by page, with chapters written in different wavelengths. The next step is close enough to touch with our instruments. We turn from our home galaxy's interior view to the nearest neighbours outside it, where the geometry is clearer and the details are sharp. There, in the local group, we test the rules before we leap into the ancient dark. We begin with the galaxies next door, where the map first becomes three-dimensional, and where the universe's vastness becomes something we can measure rather than merely imagine. We turn from our home galaxy's interior view to the nearest neighbours outside it. The local group is close enough for precision, yet large enough to reveal the rules. It becomes our Rosetta Stone for translating light into structure, motion, and history. On wide-field maps, it looks like a loose handful of islands scattered in black water, yet every island is moving, and every motion carries a record. The Milky Way is not a picture on the sky. It is a rotating system with parts that behave differently under gravity, and that difference is the first clue to its assembly. We live in its disk, embedded in gas, dust, and young stars, so our view is filtered through the very material we are trying to understand. From inside, we reconstruct the whole by mapping distances, velocities, and chemical fingerprints, turning a star's spectrum into a kind of biography. The disk is the Milky Way's thin, rotating plane of stars and gas. It holds spiral arms where density waves compress gas and trigger star formation, and where dust lanes draw dark calligraphy across the starlight. Those arms are not rigid structures. They are patterns that sweep through the disk while stars drift in and out, like cars passing through a traffic jam that moves more slowly than the traffic itself. In the arms, cold molecular clouds become the raw material for new suns. Gravity pulls gas into knots, turbulence tears it apart, and magnetic fields thread through the collapse. Three forces arguing over the same parcel of matter. When collapse wins, clusters ignite, and the brightest, most massive stars flood their birthplaces with ultraviolet light. The result is visible even from afar: pink EH2 regions, blue associations of hot stars, and the mottled glow of dust warmed by starlight. The central bulge is thicker and older, packed with stars on more varied orbits. Its light is smoother, less clumpy than the disk, because the star-forming gas is largely gone, and the stellar population is more mature. The bulge blends into a bar that stretches across the inner galaxy. The bar is not decoration. It is a dynamical engine that redistributes angular momentum and funnels gas inward, reshaping the inner disk over billions of years. Bars arise naturally in rotating disks when gravity amplifies smaller symmetries. Once established, the bar's elongated potential shepherd stars into families of orbits, some aligned with the bar and others tilted in complex ways. Gas responds differently because it can collide and dissipate energy. It shocks along dust lanes on the leading edges of the bar, dark straight streaks that mark where interstellar clouds are being compressed. That compression can feed central star formation, and it can also build dense rings near resonances. Spiral arms, bar and bulge connect through resonances that shape orbits. These are special radii where orbital frequencies line up with the pattern speed of the bar or the spiral structure. Gas clouds respond strongly, piling into lanes and shocks, because they cannot simply pass through without losing energy. Star formation follows that flow, then feedback pushes back with winds and supernovae, so the disk becomes a regulated ecosystem rather than a simple factory. Even in a calm spiral, the disk is never truly quiet. Stellar winds carve cavities, supernova remnants expand as glowing shells, and turbulence keeps the interstellar medium in constant motion. Some of that energy leaks upward, punching chimneys through the disk and venting hot gas into the halo. The disk's thinness is therefore a balancing act. Gravity pulls material inward, while feedback and orbital heating try to puff it up. Above and below the disk lies the halo, sparse in stars but vast in extent. Halo stars move on elongated, tilted orbits that ignore the disk's orderly rotation, and their paths carry them far above the galactic plane. Many of those stars arrived through mergers. Their motions and chemistry preserve the record of accretion, like shards in a geological layer that do not match the rock around them. The halo is also where the Milky Way's past becomes easiest to read. In the disk, billions of years of mixing blur the signatures of individual events. In the halo, streams can remain coherent for a long time, because orbital periods are long and densities are low. A stream is a disrupted satellite stretched into a ribbon, and its stars still remember the orbit of the system that once held them together. Stellar populations label that record. Populationist stars are metal-rich and often young, concentrated in the disk and spiral arms, where ongoing star formation keeps the chemistry evolving. Population 2 stars are metal-poor and generally older, common in the halo and in globular clusters. The difference is not cosmetic. It encodes when the gas was enriched by earlier generations, and it sets constraints on how quickly the galaxy built its heavy elements. In astronomy, metals mean almost everything heavier than helium. Those elements are forged in stellar interiors and in explosive deaths, then dispersed through winds and supernova ejecta. The earlier stars formed from nearly pristine hydrogen and helium, so they left behind descendants with very low metallicity. Later generations inherited enriched gas, and their spectra carry stronger absorption lines from iron, magnesium, calcium, and other heavy elements. Metallicity becomes a clock with caveats. Heavy elements build up as stars live and die, then seed the next stars, but enrichment is uneven and sometimes delayed. So low metallicity points to early formation, or to isolated environments that formed few stars. Gradients across the disk reveal inside-out growth, where inner regions enriched faster than outer ones, while local pockets preserve the imprint of bursts and lulls. The disk's chemical pattern is not just radial, it also changes with height above the plane, because older, dynamically heated stars tend to occupy thicker layers. This is why surveys that measure both motion and composition are so powerful. A star's orbit tells us where it has travelled, while its metallicity hints at where it was born. Together they let us test whether the disk grew smoothly or in fits, and whether mergers stirred it. At the Milky Way's centre, dust blocks visible light, but orbits do not lie. Astronomers track individual stars near the radio source Sagittarius A using infrared telescopes that can see through much of the obscuration. Over years and decades, those stars trace arcs across the sky that become closed loops when enough time passes. Their speeds rise to thousands of kilometers per second near closest approach, and that acceleration is the signature of a deep, compact gravitational well. The orbits are Keplerian at small radii, implying a compact mass. That detail matters, because a diffuse cluster of matter would produce a different orbital pattern. The tightest observed orbits swing within a region comparable to the size of our solar system, and the stars do not slow as if the mass was spread out. Gravity is pointing to a single dominant object, hidden behind dust and darkness. The inferred mass is about 4 million suns, confined within a region smaller than our solar system. No cluster of normal stars can remain that dense without evaporating through gravitational encounters or collapsing into something more compact. The simplest explanation is a supermassive black hole. It is quiet compared to quasars, but it anchors the galaxy's central potential, and it offers a nearby laboratory for testing gravity in an extreme regime. Historically, this was not an easy claim to make. The idea of massive dark objects at galactic centers matured over decades, as radio astronomy improved and infrared imaging sharpened. The clinching evidence came from patience, year after year of measuring positions until the orbits became undeniable. In a sense, Sagittarius A is a reminder that some cosmic truths are not photographed in a moment. They are measured in time. This is a key lesson for the central question. Galaxies evolve through components we can see and engines we infer, and the boundary between the two is where the mystery lives. The Milky Way's black hole is tiny in size, yet it sets boundary conditions for the inner dynamics. It also hints at a broader connection between bulges and black holes across cosmic time, a correlation that suggests coevolution rather than coincidence. Now we step outside our own system by using a mirror. Andromeda, M31, is the nearest giant spiral, similar in mass scale and complexity. It offers the external view we cannot get of the Milky Way, letting us see the overall geometry without being trapped inside the disk. It also offers a warning about what gravity does to neighbours, because its outskirts are littered with evidence of past encounters. Andromeda's disk, bulge and halo can be mapped in detail. Its inclined disk shows dark dust lanes and bright star-forming regions, while its bulge glows with older light. In long exposures, the halo emerges as a faint extended haze, and within that haze are sharp structures that do not belong to a smooth, relaxed system. Its halo is rich with stellar streams, arcs and shells, some wrapping like smoke trails around the galaxy. These are not random decorations. They are tidal debris from dwarf galaxies that were torn apart and absorbed. They're stars stretched along their former orbits. A shell can form when debris piles up near the turning points of an orbit, creating a bright edge like a ripple in a pond. A stream can persist as a thin filament for billions of years, slowly widening as stars drift apart. Those streams are evidence that large galaxies grow by cannibalism. Each stream carries a distinct orbit and chemical pattern, because each progenitor had its own star formation history and enrichment. By modelling them, we infer the shape of Andromeda's gravitational potential, including how extended and how flattened its dark matter halo may be. The halo becomes a forensic scene where gravity preserved the trajectories and where the crime is simply time. Andromeda also shows that a spiral can hide a violent past. Its stellar halo appears more massive and more structured than the Milky Way's, suggesting it may have swallowed more substantial companions. That difference may reflect different merger histories, and it is a warning against assuming that similar galaxies lived similar lives. Similar mass does not guarantee similar biography, and in cosmology, biography is often destiny. The local group's future is already written in motion. Andromeda and the Milky Way are approaching each other at over 100 kilometers per second, a closing speed measured from Doppler shifts and refined by proper motion constraints. Their mutual gravity overcomes cosmic expansion on this scale, because the local group is gravitationally bound. In about 4 to 5 billion years, the two disks will collide and merge, and the night sky, if anyone is watching, will become crowded with a growing, luminous rival. The merger will not be a collision of stars in the everyday sense. The distances between stars are enormous, so direct impacts are rare even when galaxies overlap. The real collision is gravitational. Tides will distort both galaxies, drawing out long tails of stars and gas, and compressing clouds until star formation surges, then exhausts or is blown back by feedback. As the galaxies interpenetrate, their disks will warp and thicken. Some stars will be flung onto wide looping orbits, and others will sink inward as the system redistributes energy and angular momentum. Gas, unlike stars, can collide and radiate away energy, so it tends to fall toward the center. That inflow can feed central starbursts, and it can also provide fuel for the central black holes, briefly making the remnant more active. Over time, the remnant will likely resemble a large elliptical or a puffed-up spheroid. Orbits will randomize and the tidy disk structure will be erased, leaving a smoother distribution of stars with little net rotation. The central black holes may eventually coalesce, releasing energy as gravitational waves, and the final system may settle into a new equilibrium. The local group teaches that galaxy morphology is temporary, and that even grand spirals are only a phase. Triangulum, M33, adds a third major spiral to the laboratory. It is smaller and more gas-rich, with active star formation that lights up its arms in scattered knots. Its structure is less dominated by a large bulge, so the disk's patterns are more exposed. It shows how mass and environment tune a galaxy's balance between order and turbulence, and how a lighter system can remain more visibly youthful. M33 may also be dynamically entangled with Andromeda. Its past orbit could have stirred its disk and warped its gas, leaving subtle asymmetries that act like fingerprints of an encounter. Even in a small group, galaxies do not evolve in isolation. Their histories are coupled by repeated encounters, some dramatic and some so gentle they are only revealed by careful kinematics. Around these giants swarm dozens of dwarf galaxies. Some are bright enough to be known for centuries, appearing as faint smudges in early telescopes before their nature was understood. Others are ultra-faint dwarfs, discovered only with modern surveys that can detect sparse star counts across huge areas of sky. These dwarfs are not mere satellites. They are fossils of early structure formation, and their simplicity can be an advantage. Ultra-faint dwarfs contain very few stars and extremely low metallicities. Many formed most of their stars early, then shut down, leaving behind a dim population that has changed little for billions of years. Their chemical abundances preserve signatures from the first supernovae, including unusual ratios of elements that hint at the masses and explosion energies of the earlier stars. They are among the closest analogues to primordial building blocks, made visible by proximity. Dwarfs also reveal the violence of tides. As they orbit a giant, gravitational gradients stretch them, pulling harder on the near side than the far side. Stars can be stripped into streams that wrap the host galaxy, and the remaining core becomes more diffuse. Over repeated passages, the dwarf loses mass. Its dark matter halo is peeled away, and it may dissolve entirely, contributing its stars to the host's halo. Tidal stripping is not the only environmental pressure. Satellites can be quenched, meaning their star formation shuts off, and the reasons can be layered. Some lose their gas through internal feedback, especially if early supernovae heat the gas above the escape speed. Environment often finishes the job, because repeated passages through the host's halo can remove gas and prevent fresh accretion, leaving old red populations behind. Even the host's hot halo gas can matter. A satellite moving through that thin medium feels ram pressure, a gentle but persistent force that can push gas out of the dwarf's shallow potential well. This is a quieter cousin of the dramatic stripping seen in rich clusters, but the physics is the same. The local group lets us see the early stages of that process, before the environment becomes truly extreme. This sets up a puzzle known as the missing satellites problem. Cold dark matter simulations predict many more small halos than the number of observed dwarf galaxies, especially at the lowest masses. The gap could mean many halos never formed stars, because rionization heated the intergalactic gas and made it harder to fall into small wells. It could mean we have not detected the faintest systems, because they are spread thinly across the sky. It could also point to how feedback and star formation thresholds suppress visible growth in small halos. Dwarves therefore connect local detail to cosmological theory. They test how baryons behave inside dark matter halos, where cooling, heating, and turbulence compete in a shallow gravitational field. They also test whether our model of dark matter is complete on small scales, because different dark matter properties can change how many small structures survive. The local group is close enough to count satellites, yet complex enough to challenge expectations, and that tension is scientifically productive. Underneath all these visible components lies the dominant mass. Dark matter halos envelop the Milky Way, Andromeda, and their satellites, extending far beyond the bright disks. We infer halos through dynamics, not through light, and that inference is one of modern astronomy's most consequential moves. The evidence begins with rotation curves, a deceptively simple plot of orbital speed versus radius. In a simple system where most mass is concentrated near the centre, orbital speeds should decline with distance. Planets in the solar system slow down as they orbit farther from the Sun because most of the mass sits in the Sun itself. Spiral galaxies do not follow that pattern. Their rotation curves stay flat far beyond the bright disk, implying that mass continues to accumulate with radius, even where starlight fades. An accessible analogy is a carousel in the dark. If you only see the painted horses near the centre, you would expect outer riders to move slower as the radius increases. Instead, the outer riders keep pace as if the carousel extends unseen into the darkness. The simplest reading is extra mass spread through a large halo, holding the fast orbits together and preventing the outer disk from flying apart. Gas provides a second tracer of that unseen mass. Neutral hydrogen extends beyond the optical disk, mapped by the 21 centimeter line, a radio signal produced by a subtle flip in the hydrogen atom's electron-proton spin alignment. It rotates with the galaxy and reveals the gravitational field at large radii, where starlight is too faint to guide us. The gas confirms that the visible stars are not enough, and it sketches the halo's influence in a language of radio waves. Halo mass also shapes satellite motions. Dwarf galaxies orbit too fast and too far out to be bound by starlight alone, and their internal stellar velocities often imply far more mass than their luminosity suggests. Their velocities point to a deep potential well, dominated by dark matter. In the local group, we can measure proper motions for some satellites, turning a static census into a dynamical map, and turning the halo into something we can weigh. Yet the narrative tension remains. We can resolve individual stars in nearby dwarfs, measure their metallicities, and chart their orbits with exquisite precision. Still, most of the mass is inferred, not seen, and that inference rests on the assumption that gravity behaves as we understand it. The local group is a neighbourhood where certainty and ignorance coexist in the same dataset, and where every solved measurement exposes a deeper unknown. Gas ecology adds another layer of hidden structure. The large and small Magellanic Clouds are the Milky Way's most prominent satellites, visible to the unaided eye in southern skies as luminous detached patches. They're gas-rich and actively forming stars, with bright nebulae and young clusters that stand out against their diffuse glow. Their interaction with the Milky Way and with each other creates extended features of stripped gas, drawn out like threads from a moving loom. The Magellanic Stream is a long ribbon of hydrogen trailing across the sky. It is evidence of tidal forces and ram pressure from the Milky Way's hot halo gas, and it traces an interaction that has unfolded over hundreds of millions of years. The stream is not only debris, it is potential future fuel, a reservoir that may eventually rain onto the disk, although much of it may be heated and dispersed before it can settle. Gas accretion is essential for sustaining star formation over billions of years. Without replenishment, disks would consume their cold gas and fade, because star formation is ultimately a conversion of cold, dense gas into long-lived stars. Accretion can arrive as streams, clouds, or stripped material from satellites, and it can also arrive in a warmer phase that must cool before it becomes usable. It can be heated and delayed by feedback, creating a cycle rather than a one-way flow. Feedback is the counterforce that keeps galaxies from converting all gas into stars at once. Massive stars ionize and blow bubbles in their birth clouds, and radiation pressure can help push dust and gas outward. Supernovae inject energy and momentum, driving turbulence and outflows, and enriching the surrounding medium with newly forged elements. In small galaxies, feedback can remove gas entirely. In large galaxies, it regulates the pace, keeping star formation inefficient enough to last. The local group lets us see this regulation in action. Star-forming regions in the Magellanic Clouds show clustered, bursty behavior, where a few giant molecular clouds dominate the action. Their winds carve cavities and launch material into surrounding space, creating filaments and superbubbles that glow in emission lines. The Milky Way's own disk shows superbubbles and chimneys that connect to the halo, hinting at a circulation between the plane and the surrounding medium. Stellar archaeology ties these processes to time. Globular clusters are dense, ancient star systems orbiting in the halo and bulge, and they are among the oldest luminous structures we can study in detail. Many are about 10 to 13 billion years old, dating to the early epochs of galaxy assembly. Their stars share ages and compositions that make them time capsules of early conditions, preserved by their tight gravitational binding. Globular clusters also carry clues about assembly. Some may have formed in the Milky Way's earliest collapse, when gas was dense and star formation was intense. Others may have been accreted with dwarf galaxies, arriving on distinct orbits and sometimes accompanied by streams. By combining ages, metallicities, and motions, we separate native components from immigrants, and we begin to reconstruct the sequence of events that built the halo. Metallicity gradients across the disk add another archaeological layer. Inner disk stars tend to be more metal-rich than outer disk stars, reflecting faster early star formation in the center and later growth at the edges. This suggests inside-out formation, but the pattern is not perfectly smooth. Radial migration complicates the story, because stars can move over time due to interactions with spiral arms and the bar, carrying their chemical signatures far from their birthplaces. That migration is not merely a nuisance, it is a dynamical signature of the disk's evolving structure, and it tells us that the Milky Way is not a static machine. Stars exchange angular momentum at resonances, and their guiding centers shift without necessarily heating their orbits dramatically. The disk can therefore mix chemically while still retaining gradients, a subtle interplay that modern surveys are finally able to test. Environment matters even before we reach massive clusters. In the local group, satellites experience tidal stirring that can transform rotating dwarfs into spheroidal systems, changing their shapes and kinematics over repeated orbits. They can lose gas through interactions with the host's halo, a gentler cousin of the ram pressure stripping seen in clusters later. Their star formation histories reflect both internal mass and external harassment, and their diversity becomes a map of environmental influence. Some dwarfs show extended star formation, implying they retained gas for long periods despite their small size. Others formed early and then quenched, leaving behind ancient populations with little chemical evolution afterward. The variety is a controlled experiment across mass and orbit, because the local group offers many examples under slightly different conditions. Each dwarf is a data point for how galaxies respond to their surroundings, and each one narrows the range of viable models. The local group also clarifies what we mean by a galaxy's boundary. The visible disk is not the edge of the system, and the faint halo light is only part of what extends outward. The halo reaches far beyond, filled with dark matter, sparse stars, and hot gas that is difficult to image directly. That circumgalactic medium mediates inflow and outflow, and it acts as a buffer between the galaxy and the cosmic web, where material is exchanged rather than simply kept. This brings us back to the central question. How did galaxies form and evolve from the early universe to today? The local group offers the nearest evidence that formation is hierarchical, shaped by mergers, accretion, and feedback, and that even quiet galaxies have complicated pasts. It also shows that invisible mass sets the stage, while visible matter performs within constraints, and that the performance is never fully predictable from the opening conditions. Historically, this neighbourhood calibrated our distance ladder and our models. Cepheid variables in nearby galaxies anchored extragalactic distances, because their period luminosity relation turned pulsation into a measuring stick. That calibration helped settle the scale of the universe, and it transformed faint smudges into separate galaxies with known distances. Stellar streams and satellite motions refined our understanding of gravitational potentials, and proper motions from space telescopes turned the local group into a moving system rather than a static tableau. Yet every gain in precision sharpens the mystery. We can map the Milky Way's bar and spiral pattern, but we still debate their exact shapes and speeds, and how many arms are truly persistent. We can weigh halos, but we still do not know what dark matter is, or why it behaves as it does. We can read chemical abundances in ultra-faint dwarfs, but we still struggle to connect them cleanly to the first stars, which remain beyond direct observation. The local group therefore functions as a translation key. It links resolved stars to unresolved galaxies, and local dynamics to cosmological simulations, letting us test ideas at the level of individual orbits. It tells us which features are common outcomes of gravity, and which are contingent accidents of history. It also reminds us that our home is not a stable island. It is a participant in a long chain of interactions, and its future is already in motion. Now the map expands again. We leave the local group's familiar census and move to the larger architecture that surrounds it, where the same physics plays out on grander scales. Groups gather into clusters. Clusters sit on filaments, and voids open between them, creating a pattern that is both web-like and hierarchical. The same invisible scaffolding that holds our neighbours together also shapes the distribution of galaxies across the universe, and it invites the next question: how far does the darkness reach? We carry the local group's lessons outward. Spiral structure, bars, halos, and streams become templates for interpreting distant systems where we cannot resolve individual stars. Dwarf fossils become clues to early epochs we cannot see directly, because their chemistry preserves what their light cannot. Dark matter remains the dominant actor, inferred through motion and lensing, guiding our journey into the cosmic web, where the nearest mysteries scale up into the universe's largest design. Now the map expands again. We leave the local group's close-up physics and enter the universe's large-scale architecture, where galaxies trace a pattern far bigger than any single island. The camera pulls back until familiar constellations dissolve into a dense spray of points, and the sky becomes less a dome than a volume. On the largest maps, galaxies do not spread evenly. They gather into filaments and sheets, intersect at dense nodes, and leave behind voids where almost nothing shines. From a distance, the distribution resembles a foam or a network of river deltas, bright strands outlining dark basins. This is the cosmic web. It is not a metaphor for complexity, but a measurable distribution of matter shaped by gravity over cosmic time. Its patterns can be quantified, simulated, and compared to data, which is why it feels both beautiful and unforgivingly physical. Filaments are elongated bridges of galaxies and gas. They can stretch for hundreds of megaparsecs, yet remain only a few megaparsecs thick, like cables drawn across intergalactic space. Sheets are broad, flattened regions that connect filaments, and both funnel material toward the densest intersections. At the nodes sit galaxy clusters, the web's knots. Between the knots open voids, typically tens of megaparsecs across, where galaxy density drops dramatically. In visualizations, voids read as black cavities, while filaments glow with a faint mottled grain of galaxies. Clusters are smaller than voids, but still immense. Their cores span a few megaparsecs, and their gravity binds hundreds to thousands of galaxies. Even the word cluster can mislead. These are not tight bouquets, but sprawling cities whose suburbs fade gradually into the surrounding web. The web's geometry answers a practical question. If galaxies formed from the same early universe, why do they appear in crowded cities and empty deserts? The answer is that the early universe was not perfectly uniform, and gravity is a patient amplifier of tiny advantages. The origin story begins before galaxies existed. Tiny density fluctuations were imprinted in the early universe and recorded in the cosmic microwave background. Those fluctuations were only parts in 100,000, yet they were enough to determine where matter would eventually collect. The CMB is a snapshot of a hot plasma becoming transparent. When electrons finally combined with protons to make neutral hydrogen, photons stopped scattering constantly and began to travel freely. Its temperature variations are small, but they mark where matter was slightly denser or thinner. Those mottled patches on the CMB sky are not random decoration. They encode a precise spectrum of fluctuations, shaped by early universe physics and the contents of the cosmos. In plain terms, they are the first map of where the web could grow. Gravity amplifies those differences through gravitational instability. Over billions of years, overdense regions pull in more matter, and underdense regions lose matter. A region that starts only slightly heavier becomes a deeper well, and that well attracts still more mass. This growth is not smooth in detail. It is hierarchical, with small structures collapsing first, then merging into larger halos, then assembling groups and clusters. In simulations, one can watch the process like time-lapse weather. Eddies form, merge, and harden into long-lived systems. Dark matter drives this process. It is effectively collisionless, so it streams through itself without shocks, building extended halos that dominate the gravitational potential. Because it does not radiate energy away, it does not collapse into thin disks. It stays puffy, forming the invisible framework. Baryons behave differently. Normal matter can collide, radiate energy, and cool, so it falls into dark matter wells and condenses into the gas that forms stars. Cooling depends on atomic physics, how efficiently gas can emit photons, and that efficiency changes with temperature, density, and chemical enrichment. In this view, galaxies are not the web's framework. They are the luminous tracer paint, marking where the deeper scaffolding has already formed. When we see a bright chain of galaxies, we're seeing where an even larger reservoir of dark matter and diffuse gas has already gathered. The web also explains why environment matters. A galaxy's fate depends on whether it grows along a filament, drifts into a cluster, or lives in a void. The same internal engine can produce different outcomes, because the external supply of gas and the surrounding gravitational tides are different. To see the web, astronomers first need distance in 3 dimensions. Redshift surveys turn spectra into positions, converting the sky into a volume. Each spectrum is a barcode of absorption and emission lines, and their shift tells us how fast the galaxy is receding with cosmic expansion. In a redshift survey, each galaxy contributes a point with a measured z. Millions of points reveal filaments, walls, and empty regions as statistical structure. When the points are plotted, the eye begins to recognize corridors and chambers, as if the universe were an enormous cathedral of matter. Surveys like SDSS made the web undeniable. They showed that the universe is homogeneous only when averaged over very large scales. On smaller scales, it is richly textured, and that texture is the fossil record of structure growth. There is also history in how we learn to see it. Early galaxy catalogues hinted at clustering, but the sky was a 2-dimensional projection that hid depth. Only with large systematic redshift programs did the web emerge as a coherent, repeated pattern rather than a suggestive anecdote. Yet redshift maps have a complication. Redshift includes both the Hubble flow and peculiar velocities, the local motions caused by gravity. A galaxy's observed redshift is therefore a sum of cosmic expansion and its own motion within a gravitational landscape. Peculiar velocities distort the apparent structure in redshift space. Clusters stretch into fingers along the line of sight because galaxies orbit rapidly inside deep potentials. What should be a compact knot becomes a radial smear, like a brushstroke pulled toward the observer. Those motions are not noise, they are a dynamical signal of mass, because only strong gravity can produce large random velocities in a bound region. By measuring the dispersion of speeds, astronomers infer the depth of the potential well, even when much of the mass is dark. On even larger scales, peculiar velocities reveal coherent flows. Galaxies stream along filaments toward overdensities, like water moving down a gravitational gradient. In reconstructions, arrows of motion converge toward massive regions, and the web looks less like a static map than a living circulation system. This leads to the idea of basins of attraction. Large regions of space share a common flow pattern toward a dominant concentration of mass. The boundaries between basins are subtle, more like watersheds than walls, and they remind us that gravity organizes motion over enormous distances. The web is therefore both a map and a machine. It predicts where matter should accumulate and how it should move, even when much of it stays invisible. When we chart the web, we're also charting future mergers, future infill, and the long-term redistribution of matter. Clusters are the web's extreme laboratories. They are the places where hierarchical growth becomes most dramatic and where environment reshapes galaxies quickly. In a cluster, the density of galaxies rises, the background gas thickens, and the gravitational field becomes steep and restless. A rich cluster can contain thousands of galaxies. Most of its baryonic mass is not in stars but in the intracluster medium, a hot, diffuse plasma. The galaxies are like embers floating in a much larger furnace of ionized gas. The intracluster medium reaches about 10⁻⁷ to 10⁸ Kelvin. At those temperatures it emits X-rays, revealing the cluster as a glowing atmosphere. In X-ray images, the emission is smooth and luminous, often brightest at the core where the gas is densest. The gas is heated by gravitational infall and shocks. As smaller groups fall in, their gas is stripped and mixed, building a hot reservoir that fills the cluster. The heating is a conversion of potential energy into thermal motion, and it is one of the clearest signatures of structure formation still happening. Clusters also contain dark matter as the dominant mass component. The galaxies and hot gas sit inside a much larger halo that sets the cluster's gravity. Without that halo, the observed galaxy speeds and the hot gas pressure could not be held together for long. Gravitational lensing makes that halo measurable. Background galaxies appear subtly stretched, and their coherent shear maps the projected mass distribution. The effect is tiny for any one galaxy, but averaged over many, it becomes a crisp fingerprint of the cluster's mass. Strong lensing adds a sharper signature. Near the densest cores, background galaxies become arcs and multiple images, turning gravity into a natural telescope. Those arcs trace the geometry of space-time itself, and their curvature encodes how mass is concentrated in the center. Lensing is crucial because it does not care about light from the mass itself. It measures gravity directly, exposing where dark matter is concentrated. This is one reason clusters are so valuable. Few other systems let us compare light, gas, and total mass so cleanly. This is where the chapter's tension deepens. We can map the web's mass with lensing and motions, yet the dominant component remains unseen in any direct way. The universe offers us an outline, but withholds the material that draws the line. The cluster environment transforms galaxies. Spirals are common in the field, but clusters are dominated by ellipticals and lenticulars with little cold gas. The change is visible even in colour. Blue star-forming disks give way to redder, older stellar populations. Part of the reason is RAM pressure stripping. A galaxy moving through the hot intracluster medium feels a wind that can push its cold gas out. The strength depends on speed and gas density, and in the cluster core the effect can be forceful enough to peel gas from the disk like a flag in a gale. When gas is removed, star formation fades. The disk can remain, but it becomes smoother and redder, producing a lenticular galaxy with little spiral structure. In some cases, astronomers see tails of stripped gas trailing behind, lit by newborn stars that formed during the removal. Another mechanism is harassment, rapid, repeated encounters with other galaxies, and the cluster potential heat stellar orbits and disturb disks. Each encounter is brief, but the cumulative effect can thicken a disk, stir bars, and fling stars into diffuse halos. Harassment does not require a direct merger. It is cumulative gravitational stirring, strongest where galaxy densities and relative velocities are high. In a cluster, galaxies pass each other too fast to merge easily, yet they still exchange energy through tides. Strangulation adds a slower pathway. The cluster can remove or heat a galaxy's surrounding halo gas, cutting off fresh fuel that would otherwise cool onto the disk. The galaxy keeps forming stars for a while, but it is living on savings rather than income. Without replenishment, the remaining cold gas is consumed or expelled. Star formation declines over a few billion years, even without dramatic stripping events. This slow dimming is harder to catch in a single image, yet it shapes the long-term demographics of cluster galaxies. These processes answer a version of the central question. Galaxies evolve not only by internal physics, but by where they live in the web. A galaxy's address determines how often it is jostled, how easily it can keep its gas, and how quickly its star formation is interrupted. Clusters also reveal a thermodynamic boundary. Their hot gas can prevent cooling, making it harder for new stars to form, and harder for disks to regrow. In effect, The cluster creates a high-temperature environment where gas struggles to settle into the cold, dense clouds that stars require. Yet clusters are not isolated nodes. They are fed by filaments, and those filaments deliver both galaxies and gas into the cluster's growing potential. If we could see the faint gas directly, we would watch it stream inward, guided by the web's geometry. Filaments are not just chains of galaxies, they are channels for the intergalactic medium, including gas that can accrete onto galaxies and sustain star formation. The gas is often ionized and thin, more like a mist than a cloud, yet it contains a significant share of the universe's ordinary matter. In simulations, baryons follow dark matter into filaments, then shock and heat near massive halos. Some gas remains cooler and can stream inward more efficiently. The difference matters because cooler inflows can feed star formation, while hotter gas may linger as a reservoir that is slow to condense. This is the supply line for galaxies outside clusters. Along filaments, gas can be guided into halos, cool, and settle into rotating disks. The disks we see in the nearby universe are therefore not just products of local collapse, but of long-term delivery through the web. The web therefore connects large-scale structure to small-scale star formation. It sets the boundary conditions for how much fuel reaches a galaxy and when. Even feedback, winds from stars and black holes, pushes against a supply that is shaped by the surrounding filaments. Voids show the opposite regime. They are low-density environments where mergers are rarer, tidal fields are weaker, and external stripping is minimal. In the web's negative space, galaxies live farther apart, and the gravitational landscape is comparatively gentle. A typical void spans tens of megaparsecs, and its interior can be remarkably empty. Galaxies inside are fewer, often smaller, and sometimes unusually gas-rich. When a void galaxy forms stars, it can do so with less interruption, as if time runs more quietly there. Voids can shelter dwarf and low-surface brightness galaxies. In dense regions, such fragile systems are more easily disrupted or quenched. Their survival in voids is a clue that environment can be an eraser, removing faint galaxies from crowded regions over cosmic time. Void galaxies become tests of nature versus nurture. If a galaxy is isolated yet still quenched, internal processes must be sufficient to shut it down. That might mean stellar feedback, the exhaustion of gas, or the inability of a small halo to retain material after heating. If an isolated galaxy stays gas-rich and star-forming, environment may be the main driver of quenching in denser regions. The contrast becomes a natural experiment, with voids as control samples and clusters as stress tests. Voids also challenge observation. Low-surface brightness systems can be missed in flux-limited surveys, so the emptiness can be partly a selection effect. The very galaxies that would soften the void's darkness are the ones most likely to slip below detection thresholds. Even so, void statistics are powerful. Their size distribution and galaxy content constrain cosmological models and the growth rate of structure. In simulations, changing the matter density or the strength of clustering changes the abundance of large voids, making them sensitive probes of the cosmic recipe. To quantify the web, astronomers use correlation functions and power spectra. These statistics measure clustering strength as a function of scale. They translate the visual impression of filaments and voids into numbers that can be compared across surveys and epochs. One feature stands out across surveys. Baryon acoustic oscillations imprint a preferred separation scale, a relic of sound waves in the early plasma. Before the universe became transparent, pressure waves travelled outward from overdensities, leaving a subtle ring-like preference in the later distribution of galaxies. BAO acts as a standard ruler. By measuring its apparent size at different redshifts, we infer the expansion history that stretched the ruler over time. The ruler is not carved into space as a line, but encoded statistically in how often galaxies appear at certain separations. This ties the web to cosmology directly. The same early physics that set the CMB fluctuations also set the seeds for the web's later pattern. When we measure BAO today, we are reading a message sent from the plasma era and delivered through billions of years of expansion. Lensing shear adds another tool. Weak lensing surveys map the integrated mass distribution, tracing dark matter even where galaxies are sparse. The method is demanding because it requires exquisite control of image distortions, yet its reward is a mass map that does not depend on luminous traces. When redshift surveys and lensing maps are combined, the picture sharpens. Galaxies trace peaks in the mass field, but but they do not trace it perfectly. Some halos host bright galaxies, others host faint ones, and feedback can change the relationship between mass and light. Bias becomes part of the story. Different galaxy types cluster differently because star formation and feedback respond to halo mass and environment. Red, quenched galaxies tend to sit in denser regions, while blue, star-forming galaxies more often outline filaments and lower density outskirts. The web is therefore a joint product. Gravity sets the skeleton, baryonic physics paints the luminous details, and observation must disentangle both. The challenge is not only to map where galaxies are, but to infer what the galaxies are failing to show us. This disentangling exposes another absence. Even among baryons, much of the normal matter is not in stars or cold gas that is easy to detect. The accounting from primordial nucleosynthesis and the CMB predicts a certain baryon density, yet nearby inventories come up short. The missing baryons problem is not about dark matter. It is about ordinary matter predicted by cosmology that is difficult to find in galaxies and clusters. The matter is not necessarily gone. It is likely hiding in phases that are too hot, too thin, or too diffuse to glow brightly. A leading reservoir is the warm-hot intergalactic medium. It is gas at roughly 1005 to 10^7 Kelvin, spread thinly through filaments and outskirts. In this range, hydrogen is ionized and the emission is weak, so the gas is more easily detected by what it absorbs than by what it radiates. At those temperatures and densities, it is faint. It can be traced by ultraviolet and X-ray absorption lines against bright background sources. Quasars become flashlights, and the intervening web becomes a barely visible fog that leaves narrow notches in the spectrum. The web should contain this material because shocks and feedback heat gas as it falls into filaments and halos, yet detecting it is observationally hard. The signals are subtle, the lines can be blended, and the background sources are rare, which makes every detection feel like a difficult excavation. So the web becomes a mystery in two layers. Dark matter shapes the structure we measure with lensing, and missing baryons may hide in the same filaments. The luminous galaxies are only the brightest beads on a much larger, mostly invisible thread. This matters for galaxy evolution. If the missing baryons sit in warm-hot phases, they represent the fuel reservoir that can later cool or remain locked away. The difference between a galaxy that keeps forming stars and one that fades may depend on whether that reservoir can condense back into cold gas. It also matters for the central question. Galaxies are not closed boxes, and their histories depend on exchanges with the surrounding medium we barely see. Every burst of star formation, every outflow and every quiet decline is part of a larger circulation between galaxies and the web. The cosmic web also clarifies why the universe looks the way it does today. Gravity amplifies early fluctuations, but expansion competes by stretching space. The web is the compromise between attraction and dilution, a pattern that grew while the universe kept getting bigger. Structure growth depends on the balance between matter density and cosmic acceleration. The web's present pattern encodes that balance in its clustering. When acceleration dominates, growth slows, and the web's strands stop thickening as quickly as they once did. In the nearby universe, we can measure growth through redshift space distortions and lensing. Those measurements test gravity on the largest accessible scales. They ask whether the same rules that govern planets and stars also govern the formation of the larger structures we can map. If growth differs from predictions, the implications are profound. It could point to new physics in dark energy, or to modifications of gravity itself. The web becomes not only a structure to admire, but a laboratory for fundamental laws. For now, the simplest model still works well. Cold dark matter builds halos. Halos merge hierarchically, and baryons light up where cooling succeeds. The web seen in surveys broadly matches the web grown in simulations, which is a rare and powerful alignment between theory and observation. Yet the simplicity is deceptive. Feedback from stars and black holes can heat gas and expel it, changing how efficiently halos turn baryons into galaxies. That feedback can also reshape the gas in filaments and cluster outskirts, complicating the clean picture of matter simply flowing downhill. The web sets the stage for those feedback loops. Dense nodes trap hot gas and suppress cooling, while filaments can deliver fresh material to less massive halos. The same network that feeds galaxies can also carry away the consequences of their own activity, spreading energy and metals into the surrounding medium. We can now restate the chapter's core claim. The web predicts where galaxies should be, but the web is mostly invisible matter and faint gas. What we see is only the bright fraction, and even that fraction is shaped by environment and history. We see the luminous traces and infer the rest. Every map of galaxies is therefore also a map of what we cannot see, drawn in negative space. The voids are not merely empty, they are regions where the initial conditions and subsequent flows left behind a different fate. This is why the cosmic web feels like an answer and a riddle. It is a coherent pattern, yet its dominant ingredients remain hidden from direct detection. The more precisely we map the structure, the more clearly we confront what is missing from our senses. The next move is to follow the web backward in time. Redshift is not only distance, but an earlier epoch when filaments were thinner and clusters less mature. Looking deeper means looking younger, when the web's strands were still being pulled taut. At higher redshift, the web is still assembling. Nodes are forming, gas is colder on average, and the first galaxies are beginning to ignite inside young halos. The contrast between bright and dark is weaker, and the network is more delicate, as if the universe is still sketching the lines. We transition from the present-day web to the deep past. We follow redshift back to the first galaxies, when the scaffolding existed but the lights were just turning on. The question is no longer only where galaxies are today, but when the first ones began to mark the web at all. The journey continues by asking a sharper question. If dark matter drew the web's shape, when did the first luminous galaxies begin to trace it? Did the earlier stars ignite preferentially along filaments? And did the first nodes already hint at future clusters? We move from the web we can map in millions of galaxies to the era when only a few existed. There, the universe's structure is still real but barely glowing. In that dim beginning, the cosmic web is present as gravity's blueprint, waiting for light to catch up. We transition from the present-day web to the deep past, where the scaffolding existed before the lights. Redshift becomes our time machine again, pushing beyond familiar galaxies into the first billion years. The central question sharpens here, because the timeline feels almost impossible when we translate it into physics. How did galaxies form so quickly, and how did their hidden structures set our own origin story? Begin with a universe that was once too hot for atoms, a seething plasma where nuclei and electrons could not stay together. In the first minutes, Big Bang nucleosynthesis built mostly hydrogen and helium, with trace lithium and a few rare isotopes. The ratios mattered, because they became a baseline that later generations could only modify, never erase. For hundreds of thousands of years afterward, matter stayed ionized, and photons scattered constantly off free electrons. Light could not travel far, so the cosmos behaved like a glowing fog with no horizon. Then recombination arrived around 380,000 years after the Big Bang, when temperatures fell enough for electrons to settle onto protons. Neutral hydrogen formed in bulk, and the mean free path of photons suddenly grew enormous. The cosmic microwave background is the afterglow of that moment, an all-sky photograph of the universe becoming transparent. On screen it can look like mottled static, yet those tiny temperature variations are a map of primordial density ripples. They are small in amplitude, but they are decisive in consequence. Those ripples are not decorative noise because gravity treats them like seeds. Slightly denser regions pull in more matter and slightly emptier regions lose it, so contrast increases with time. Dark matter, which does not couple to light, begins clumping even earlier and more efficiently than ordinary gas. By the time atoms form, much of the gravitational architecture is already in place, invisible but active. The cosmic web is not a late invention. It is the early universe's default outcome once expansion and gravity begin their long negotiation. After recombination, the universe entered the Dark Ages, a period that is dark in the literal sense. Space was filled with neutral hydrogen and helium, and there were no stars yet to ignite the gas. If we could see in radio wavelengths, we would watch hydrogen's 21 centimeter signal tracing vast sheets and filaments. Visually, though, this era is a near black ocean with only the faintest background glow. The web is present, but it has no lanterns hanging from it. Gravity kept amplifying tiny density fluctuations, building halos that could one day host galaxies. These halos form a hierarchy, from small to large, because small scales collapse first in cold, dark matter models. Baryons followed those wells, but they did not fall in freely, because pressure and residual heat resisted compression. Gas had to cool before it could collapse further, and cooling is never automatic. The first light depends on whether the universe can shed energy fast enough to concentrate matter into stars. Cooling is the first gatekeeper of first light, and its rules are set by quantum mechanics. In pristine gas, atomic hydrogen cools efficiently only above about 10,000 Kelvin, when collisions can excite electrons into higher energy states. When those electrons drop back down, they emit photons that carry energy away, and the gas temperature falls. Smaller halos stayed too warm and too diffuse, unable to radiate away their heat quickly enough. They could gather gas, yet they could not turn that gas into dense, star-forming clouds. Molecular hydrogen offered another path, letting gas cool to a few hundred Kelvin in the earliest mini-halos. H2 forms through a delicate sequence of reactions that often requires intermediate ions, because dust grains are not yet available. That chemistry is slow, but even a small H2 fraction can change the thermal history of a cloud. Cooler gas means lower pressure, and lower pressure means gravity can win at smaller masses. The pathway was fragile because ultraviolet radiation can break H2 apart and shut the channel down. This fragility introduces a suspenseful feedback loop, because the first stars both require molecules and threaten them. Once a few stars ignite, their ultraviolet photons can travel far in a still thin universe. Those photons dissociate molecular hydrogen in neighbouring halos, raising the minimum mass needed for cooling. The first light can therefore delay more light, at least temporarily, by changing the chemistry of its surroundings. It is a reminder that cosmic history is not a smooth ramp. It is a chain of thresholds. This is where population 3 stars enter as a hypothesis with consequences, a predicted first generation rather than a confirmed cast of characters. They formed from nearly metal-free gas, so cooling was limited and fragmentation was different. With fewer ways to radiate energy, collapsing clouds may have stayed warmer and broken into fewer pieces. Many models predict these stars were massive and short-lived, though the true mass distribution remains uncertain. Some simulations allow a broader range, including lower mass survivors, but the evidence is indirect. We have not seen a confirmed population 3 star directly, because they would have died quickly and their light is far away. Even if one survived at low mass, it would be rare and difficult to identify among billions of later stars. Yet their fingerprints may survive in the chemistry of ancient stars in our own galaxy's halo. When astronomers find extremely metal-poor stars, they are reading a fossil record of early enrichment. The question becomes almost forensic. What kind of explosion left this particular pattern of elements? The first stars were not just lights. They were engines that changed the universe's chemistry and ionization state, and they did it on short, dramatic timescales. In their cores, fusion built heavier elements up to carbon and oxygen, and later stages forged still heavier nuclei. The details depend on mass, rotation, and internal mixing, which alter how quickly fuel is consumed. When the most massive ones died, they exploded as supernova and scattered those new metals into surrounding gas. Some may have ended as direct collapse black holes, seeding later growth in galactic centers. In visuals, imagine a dark halo filling with gas like mist pooling in a valley, then a sudden flare as a star ignites. The flare is followed by expanding shells, shock fronts that sweep outward and compress some regions while evacuating others. That outward motion is not only spectacle, it is a mechanism for redistributing matter, energy, and chemical complexity across space. Metals changed everything because they changed cooling, and cooling changes what kinds of stars can form. Even tiny metallicities add new emission lines that let gas radiate energy more efficiently through fine structure and forbidden transitions. Carbon and oxygen, in particular, provide strong cooling channels at temperatures where hydrogen becomes inefficient. Dust grains can also form from heavy elements, providing surfaces that help molecules assemble and cool. With better cooling, gas fragments into smaller clumps and can form lower mass stars more like those we see today. Chemical enrichment is therefore a feedback loop between stellar death and future star birth. Each generation modifies the next generation's starting conditions, which means the universe gradually becomes better at making long-lived stars. That shift is not merely a change in stellar demographics. It alters how galaxies shine, because massive stars dominate ultraviolet light while low-mass stars store mass for billions of years. The first galaxies are shaped by which kind of star formation is thermodynamically favoured. In a sense, chemistry sets the galaxy's personality. The first galaxies emerged hundreds of millions of years after the Big Bang, when enough halos crossed key thresholds and began sustained star formation. They formed inside dark matter halos that gathered gas at increasing rates as the universe evolved. Hierarchical build-up meant small halos formed first, then merged into larger systems, and that merging never truly stops. Early galaxies were not settled spirals with long-lived disks. They were assembling under rapid inflow, frequent interactions, and intense bursts of star formation. When we picture them, we should resist the temptation to imagine miniature versions of the Milky Way. Their stellar populations were young, their gas fractions were high, and their gravitational potentials were still deepening. Star-forming regions could dominate the entire appearance because there was little older starlight to smooth the scene. In images, the background is faint and the bright parts look like scattered embers. The galaxy is less a calm island and more a storm system. This is why early galaxies look irregular and clumpy, even when they are not being torn apart. High gas fractions made their disks turbulent and thick, with large gravitational instabilities that can form massive star-forming complexes. Instead of smooth spiral arms, star formation concentrated into giant clumps that dominated the light. Astronomers call some of these systems clump clusters, where a few bright knots sit in a faint, messy background. The clumps can migrate inward over time, potentially building central bulges as they lose angular momentum. Frequent mergers and flybys further disrupted symmetry, because the universe was denser and encounters were more common. Relative velocities were often lower than in today's expanded cosmos, which can make mergers more effective at reshaping structure. Tidal forces stretch gas and stars into streams, then fold them back into new configurations. Even when a merger is minor, it can stir turbulence and trigger fresh star formation. The irregularity is therefore not an aesthetic detail. It is a signature of a crowded, rapidly evolving environment. Gas inflows fed this chaos, and the cosmic web acted like a supply network. Along filaments of the young cosmic web, cold streams could penetrate halos and deliver fresh fuel. These streams can remain relatively cool, because their densities and radiative losses allow them to avoid shock heating in certain mass ranges. Inflow rates were high compared to galaxy mass, so growth was fast and often unsteady. Angular momentum was still being sorted, and disks could be rebuilt after disturbances. The visible irregularity is not only a shape, it is a record of rapid assembly under changing gravitational tides, written into the distribution of bright star-forming knots. If we could speed up time, we would see clumps brighten and fade, streams arrive in pulses, and outflows punch holes through the gas. The galaxy is not a static object. It is a dynamic flow pattern, briefly stabilized before the next perturbation arrives. Star formation physics sets the pace, and feedback sets the brakes. So the story becomes a contest between collapse and disruption. Gas collapses when gravity wins over pressure, turbulence, and magnetic support. And that competition is often summarized by the Jeans criterion. Cooling allows collapse to continue, and fragmentation sets the characteristic mass scale of star-forming clumps. In early galaxies, turbulence was strong, so clouds were massive and collapse could be bursty. The result was intense star formation in compact regions, with short timescales and high surface densities. Those conditions also change how ionizing radiation propagates. Dense, dusty regions can trap ultraviolet photons, while low-density channels can act like escape routes. The geometry matters, not just the total amount of star formation. A galaxy can be luminous yet sealed, or modestly luminous yet porous. This is one reason ionization remains uncertain, even with improving observations. Then feedback pushes back, and it does so through multiple physical channels that operate on different clocks. Massive stars emit ultraviolet radiation that ionizes surrounding gas and heats it, raising pressure and slowing accretion. Stellar winds inject momentum and carve cavities, disrupting dense clouds before they can form many more stars. Supernovae arrive quickly, driving shocks that stir turbulence and can launch outflows. In shallow potentials, outflows can remove a large fraction of gas and delay the next burst. Even in deeper halos, feedback regulates efficiency, preventing gas from turning into stars too rapidly. Without regulation, galaxies would convert their gas into stars on a freefall timescale, and the universe would look very different today. Feedback also shapes the circumgalactic medium, the reservoir that surrounds galaxies and mediates inflow and outflow. That surrounding gas is not a passive halo. It is a battleground where cooling and heating compete. Feedback also spreads metals, but not evenly. and this unevenness is crucial for interpreting early spectra. Enrichment is patchy, because winds and explosions mix some regions while leaving others nearly pristine. Turbulent mixing takes time, and the early universe does not always grant time. This creates chemical diversity within and between early galaxies, even at the same mass. Some pockets can form stars with very low metallicity, even after enrichment begins elsewhere. The early universe becomes a mosaic of conditions, which is why simple averages can mislead. A single metallicity value can hide a distribution that spans orders of magnitude. A single star formation rate can hide bursts separated by quiet intervals. When we observe a galaxy at high redshift, we capture a moment that may not be typical of its longer history. The challenge is to infer the unseen timeline from a single frame. Astronomers read these conditions through spectral fingerprints, because light carries the physics of its source encoded in wavelength. Emission lines from ionized gas reveal temperatures, densities, and ionization states, and they can also indicate the hardness of the radiation field. Absorption lines in starlight and galaxy continue to trace chemical abundances and kinematics, including outflows that imprint blue-shifted features. Metallicity estimates come from ratios of lines like oxygen, carbon, and nitrogen, though calibrations vary and uncertainties remain. The spectrum is a compressed biography, telling us how many stellar generations have already lived and died. It is worth remembering how recent this ability is in historical terms. For much of the 20th century, the early universe was a theoretical landscape with few observational anchors. The discovery of the cosmic microwave background in 1965 transformed cosmology into a precision science, and later surveys mapped large-scale structure in exquisite detail. Yet the first galaxies remained elusive, because their light is faint and stretched into infrared wavelengths. The story of first light is also a story of instrumentation catching up to theory. Redshift adds another layer to that biography, because it changes what our telescopes must be built to detect. As we look to higher Z, the same spectral features shift into infrared wavelengths, and the sky background and detector noise become more challenging. The Lyman alpha line and the Lyman break move out of visible light, demanding infrared detectors with careful calibration. This is why the first galaxies became accessible only when infrared astronomy matured. The universe hides its earliest chapters by stretching their light beyond our natural vision. One of the most powerful tools is the dropout technique, which turns that stretching into a selection method. Neutral hydrogen absorbs photons shortward of the Lyman limit, creating a sharp break in a galaxy's spectrum. In broad filters, that break makes a galaxy disappear in one band while remaining visible in redder bands. By selecting these dropouts, surveys find candidate galaxies at specific redshift ranges. Spectroscopy then confirms redshift and reveals line diagnostics, though the faintness makes confirmation difficult. In visuals, we can show a grid of coloured filters sliding across a spectrum, then a galaxy blinking out in blue and reappearing in red. The effect feels like a magic trick, but it is physics. Hydrogen's absorption edge acting like a cosmic curtain. Still, the method has pitfalls, because dusty low redshift galaxies can sometimes mimic similar colours. The candidate lists are powerful, yet they require careful vetting. Gravitational lensing becomes a natural telescope in this regime, and it is one of the most cinematic tools in observational cosmology. Massive clusters bend space-time and magnify background galaxies, boosting their apparent brightness and stretching their images into arcs. Lensing lets us probe intrinsically fainter galaxies than direct surveys can reach, including those that may dominate the early ultraviolet budget. It also complicates interpretation, because magnification must be modelled and can vary across the field. Still, lensing opens a window onto the faint end of the galaxy population. That faint end matters because rionization demands photons in bulk, not just a few spectacular beacons. After recombination, most intergalactic hydrogen was neutral, and it absorbs ultraviolet light efficiently. Yet by about 1 billion years after the Big Bang, much of the intergalactic medium became ionized again. This is reionization, a phase change driven by ultraviolet radiation that stripped electrons from hydrogen. The exact timing and topology remain model-dependent, often placed roughly across redshifts Z about 6 to 10. Reionization is not merely a checkbox on a timeline, it alters how gas collapses into galaxies, because ionized gas is hotter and resists gravitational capture in small halos. It also changes how we observe the early universe, because neutral hydrogen absorbs Lyman alpha photons and suppresses a key emission line. In other words, reionization both shapes galaxies and hides them. The universe modifies its own transparency as it evolves. The evidence is partly written as an absence. In spectra of high redshift quasars, the gun, Peterson trough, appears when neutral hydrogen absorbs nearly all flux blueward of Lyman alpha. A deep trough indicates a significant neutral fraction along the line of sight, even if that fraction is only a few percent. By Z around 6, the trough becomes common, implying the tail end of reionization. Earlier than that, the increasing opacity suggests a universe still transitioning from neutral to ionized. We can visualize this as a bright quasar spectrum with a sudden cliff, where the blue side falls into darkness. The cliff is not a property of the quasar. It is the intervening hydrogen, acting like a fog bank that thickens with distance. Each quasar sightline samples a narrow tunnel through the cosmos, so the picture is incomplete. That incompleteness is part of the mystery. The mystery is who provided the ionizing photons and why the process completed when it did. Early star-forming galaxies are the leading candidates, because they were numerous and produced ultraviolet light through massive stars. Quasars and accreting black holes could contribute, but their observed numbers at very high redshift may be too small to dominate. The key uncertainty is the escape fraction, the share of ionizing photons that leak out of galaxies into intergalactic space. Dense gas and dust can trap radiation, so the brightest galaxies are not automatically the most effective ionizers. Reionization is therefore a balance of production and leakage, and that balance depends on small-scale structure we cannot easily resolve. It depends on how many galaxies exist below our detection limits, and how porous their interstellar media are. It also depends on recombination in the intergalactic medium, which can neutralize hydrogen again if densities are high. Clumpiness matters because denser regions recombine faster and require more photons to stay ionized. The process likely proceeded in patches, with ionized bubbles expanding and merging over time. Imagine those bubbles as faint growing cavities in a dark hydrogen sea, each one centered on a cluster of young galaxies. Some bubbles remain isolated for a while, then suddenly connect, and the topology changes rapidly. At the boundaries, neutral and ionized regions interleave like weather fronts. The universe becomes a patchwork of transparency, and our observations depend on where our line of sight passes. This patchiness is why reionization is difficult to summarize with a single redshift. Early galaxies sit inside dark matter halos that set the boundary conditions, and halo mass becomes a kind of gate. Halo mass determines whether gas can fall in, cool, and resist being blown out by feedback. Below certain masses, heating from the ultraviolet background during reionization can suppress accretion and quench star formation. Gas that might have formed stars instead remains diffuse, unable to settle into the halo's center. This connects reionization to the missing satellites problem introduced earlier. Many small halos may exist but remain dark because the universe itself became hostile to their cooling. The same ultraviolet photons that reionize the intergalactic medium also raise the temperature floor for future collapse. This is a cosmic irony. The light that reveals structure can also erase potential galaxies from visibility. When we count galaxies at high redshift, we are counting survivors of a changing radiation environment. The census is shaped by physics, not only by detection limits. Hierarchical merging continues through this era, and mergers are both constructive and destructive. Small halos merge into larger ones, bringing stars, gas, and black holes together. Mergers can trigger starbursts by compressing gas and driving inflows toward galactic centers. They can also thicken disks and scramble morphologies, reinforcing the irregular look of early systems. The cosmic web is not only a map of where galaxies are, it is a conveyor belt of future collisions. As halos merge, their dark matter components relax through violent relaxation, while gas can shock, cool, and settle again. That difference matters, because gas remembers dissipation and dark matter does not. The result is a galaxy that can rebuild a disk even after a disruptive event, provided fresh inflow continues. Early galaxies therefore oscillate between order and disorder. Their shapes are temporary compromises. Dust arrives earlier than once expected, and it changes what we can see in ways that are both frustrating and revealing. Dust forms from heavy elements in supernova ejecta, and in winds from evolved stars, though the timescales are debated. Some dust may be destroyed by shocks, while some may grow by accreting material in dense clouds. Observations of some high redshift galaxies show substantial dust reservoirs surprisingly soon. That implies rapid enrichment and efficient dust production, even when the universe was young. Dust absorbs ultraviolet and optical light, hiding star formation from direct view. Yet it also re-radiates energy in the far infrared and submillimeter, revealing obscured activity through a different window. On screen, we can shift from a dim ultraviolet view to a glowing infrared map, where the same galaxy suddenly looks massive and energetic. The energy was always there, but it was redistributed into longer wavelengths. Dust turns a galaxy into a kind of cosmic lantern shade. This creates a second observational tension. The galaxies most important for reionization should be ultraviolet bright and relatively unobscured, because dust would trap ionizing photons. Yet some early systems are already dusty and luminous in the infrared, implying intense star formation behind thick screens. The early universe contains both transparent and hidden growth, and surveys must combine ultraviolet, infrared, and submillimeter views to avoid a biased census. Each wavelength regime is a different compromise between sensitivity and physical interpretation. Spectral diagnostics help separate these populations, but they also introduce their own ambiguities. Ultraviolet slopes can indicate dust attenuation, though age and metallicity can mimic similar colors. Infrared luminosity traces dust-heated star formation, but can miss low-dust systems entirely. Emission lines like O3 and H-beta can dominate broadband fluxes at high redshift, complicating photometric estimates. Interpreting early galaxies becomes an exercise in disentangling overlapping signals from stars, gas, and dust. There is also a subtle point about what lines mean in extreme conditions. High ionization parameters can boost certain oxygen lines, making galaxies appear unusually bright in specific filters. Low metallicity can harden stellar spectra, changing the balance of line strengths. When we infer star formation rates, we are translating light into mass conversion, and the translation depends on assumptions. The early universe tests those assumptions because its conditions differ from the nearby galaxies that trained our calibrations. Chemical enrichment can also be tracked through line ratios and absorption systems, which sample gas beyond the visible stellar body. Damped Lyman alpha systems and metal line absorbers in quasar spectra probe gas outside galaxies, including the circumgalactic medium and intergalactic filaments. They reveal that metals spread into the circumgalactic and intergalactic medium early. This is feedback on cosmic scales, where outflows seed the web with heavy elements. The distribution of metals becomes a tracer of how far early winds travelled and how efficiently galaxies exchange material with their surroundings. In visual terms, we can imagine a galaxy as a bright core surrounded by faint, expanding halos of enriched gas. Those halos are not easily photographed, yet they leave signatures in absorption like invisible fingerprints. Each absorber is a waypoint in the journey of matter, from star to supernova to wind to web. The web becomes chemically annotated over time. Even emptiness acquires a history. All of this loops back to the central question, because the early universe is a laboratory for galaxy formation under extreme constraints. Galaxies evolve through a negotiation between gravity's scaffolding and baryonic physics that can cool, ignite, and explode. In the first light era, that negotiation is fast and unstable, producing clumps, bursts, and outflows. The hidden structures are not only dark matter halos, they are also ionized bubbles, metal-enriched winds, and dust screens that reshape what light can escape. It is worth pausing on what hidden really means here. Dark matter is hidden because it does not emit or absorb light in the usual ways, yet it dominates mass. Ionized bubbles are hidden because they are volumes of altered transparency, visible mostly through their effects on spectra. Metal-enriched winds are hidden because they are thin and diffuse, easier to detect in absorption than in emission. Dust screens are hidden because they hide something else, while quietly glowing in wavelengths we learn to observe only recently. Yet we must admit a limit. We can see first light, but not the first moment, and that difference matters for how confident we can be. The earlier stars are inferred from theory and from indirect chemical clues, not photographed as individuals. The faintest galaxies that may dominate reionization sit near or below detection thresholds, and lensing samples only small areas. Even redshift measurements can be biased by which lines are visible through neutral hydrogen absorption. Our origin story is written in nearly invisible ink, and we read it by combining imperfect pages. that limitation invites a deeper question. When we reconstruct an epoch from fragments, how much of the narrative is discovery and how much is interpretation? Every model is a bridge between data points, and different bridges can fit the same shoreline. The early universe often gives us silhouettes more often than full portraits. The silhouettes are beautiful, but they demand humility. Uncertainty is not a flaw here. It is the narrative engine of this epoch because each new detection shifts the boundary of what is plausible. If early galaxies are more abundant, reionization becomes easier, but demands efficient star formation in small halos. If they are rarer, escape fractions or alternative sources must rise, and models strain in different ways. The same data can support multiple histories because the universe offers us partial views shaped by selection effects. Still, a coherent picture is emerging, and it is compelling in its consistency across methods. Dark matter halos assemble hierarchically, pulling in gas along filaments that define the cosmic web. Cooling and fragmentation ignite the first stars, which enrich and disturb their surroundings with radiation and explosions. Early galaxies grow through inflow and merging, appearing clumpy because turbulence and gravity operate at high intensity. Their ultraviolet light rionizes the intergalactic medium in a patchy transition, while dust and metals complicate what we can see. In the mind's eye, the sequence is almost cinematic. First, a dim afterglow fills the frame, then darkness settles, then isolated sparks appear. Those sparks multiply into clusters, and the darkness between them begins to thin as ionized regions expand. The web that was once only gravity becomes a web traced in light. The universe learns to illuminate itself. Now the journey must follow what happens when wild growth meets crowded neighborhoods. As galaxies gain mass, their encounters become more consequential, and their mergers begin to reshape structure on larger scales. The next chapter turns from first light to cosmic choreography, where collisions trigger fireworks and build the galaxies we recognize. We move from the dawn to the dance, where assembly becomes a visible repeating pattern across time. Galaxies do not evolve only by making stars in quiet disks. They evolve by meeting, pulling, merging, and sometimes erasing their own past. In deep time, the universe does not merely expand, it rearranges, and galaxies are among its most dramatic rearrangements. When we watch the sky, we see snapshots. When gravity watches, it sees trajectories and long-term consequences. In the cosmic web, gravity is not a background force. It is choreography that keeps bringing galaxies into the same rooms. Filaments act like luminous highways, and nodes act like crowded intersections where encounters become difficult to avoid. On the larger scales, matter flows down gravitational gradients, so even isolated galaxies are often drifting along invisible streams. Collisions are common because galaxies have large gravitational cross-sections. Their dark matter halos extend far beyond the visible starlight, so the true target is larger than any optical image suggests. Those halos are not decorative. They dominate the mass budget and set the encounter's reach. Groups and filaments keep them close enough for repeated encounters, and repeated encounters make capture more likely. Even when two galaxies miss each other by tens of thousands of light-years, gravity still reaches across the gap. A near pass can bend trajectories, siphon orbital energy, and set up a future merger that unfolds over several orbits. What looks like a single event in a photograph is often a long negotiation in space-time. The galaxies may loop, recoil, and return, as if testing each other's mass before committing. The paradox is that galaxies overlap, yet their stars almost never collide. The separations between stars are so vast that most pass through untouched. If you shrank a star to the size of a grain of sand, the next grain might still be kilometers away, and that emptiness is the reason mergers are mostly collisionless. In other words, the crash is not a pileup of suns, but a reshaping of orbits. What collides is the gravitational field and the gas. Tides stretch stellar orbits, and gas clouds slam, shock, and radiate away energy. Stars behave like test particles in a changing potential, while gas behaves like a fluid that can compress, cool, and lose momentum. That difference between collisionless stars and dissipative gas is why mergers can both scramble structure and ignite new light. This is why an encounter can look gentle and still be transformative. The visible damage is often delayed, unfolding over hundreds of millions of years. Gravity plants the disturbance early, yet the galaxy takes time to display it, like ripples spreading across a pond after the stone has already sunk. By the time we see the distortion clearly, the decisive exchange of energy has already happened. In wide-field images, the first evidence is written in tidal features. Tails, bridges, shells, and streams act like fingerprints of a recent interaction. They are faint and fragile structures, and their very existence tells us the encounter was recent enough that the universe has not yet erased the trace. With deep exposures, the outskirts brighten into a ghostly map, revealing where stars have been pulled from their old homes. Long tidal tails trace the exchange of angular momentum and energy. They reveal how easily stars are lifted from a disk's ordered rotation. In simulations, tails form when the encounter geometry resonates with the disk, and the disk's outer stars are the first to be unbound. Prograde encounters, where the orbital motion aligns with disk rotation, tend to draw out the longest, cleanest tails. Visually, these tails can stretch for hundreds of thousands of light years. They arc like pale ribbons against the black, often studded with blue knots, where gas has collapsed into new star clusters. Sometimes the tail ends condense into tidal dwarf galaxies, small, self-gravitating clumps born from recycled material. In ultraviolet light, those knots can look like sparks thrown from a grinding wheel, marking where pressure and gravity briefly agree. Bridges connect galaxies that are still bound in a shared orbit. They show matter being transferred through a changing gravitational potential. A bridge can be both a conveyor and a confession, revealing that the pair has already exchanged mass and momentum. The bridge also hints at timing, because it tends to be most prominent near close passage, when tidal forces peak. In a time-lapse view, bridges look like taffy pulled between two spinning plates. Gas and stars stream along the connection, and the pattern shifts as the galaxies swing through pericenter and then drift apart again. The bridge is not static. It is a snapshot of a gravitational argument still in progress. In some systems, the bridge becomes a channel for fresh gas, feeding star formation in places that were once quiet. Shells and ripples around smooth galaxies point to past accretion. They often come from a smaller companion disrupted on a radial orbit. As the satellite stars wrap around the remnant, they pile up at turning points, creating sharp-edged arcs that resemble ripples on a cosmic shoreline. The sharpness is a clue, because it means the stars have not yet fully mixed into a smooth halo. These shells are especially striking because they appear around galaxies that otherwise look calm. The host may be a featureless elliptical invisible light, yet the outskirts tell a different story, one of repeated infall and incomplete mixing. The serenity is real, but it is also recent. When the light is stretched and the contrast is pushed, the galaxy's quiet exterior becomes a layered record of past disruption. Thin stellar streams are especially diagnostic. Their narrowness preserves orbital information before phase space mixing smears the structure. A stream is the remnant of a once coherent system, stretched by tides into a filament that still remembers its original orbit. The stream's width reflects the original satellite's internal velocity dispersion, which is a plain language way of saying how tightly it once held itself together. Phase space mixing is the universe's way of smoothing. Small differences in orbital period cause stars to spread out, and eventually the stream becomes a diffuse cloud. Yet for a long time the stream remains cold in velocity space, and that coldness is a clue we can measure. Even when the stream fades in brightness, its shared motion can persist like a melody that survives after the instruments fall silent. These features also expose hidden mass. The shapes and lengths of tails depend on the depth and extent of dark matter halos. A more massive, more extended halo can hold onto material more strongly, shortening tails and changing their curvature. Conversely, a lighter halo allows debris to fly farther, making the interaction look more flamboyant at large radii. The galaxy's response is therefore a probe of what we cannot see directly. The interaction becomes a test of the halo that guides it. By matching observed debris to numerical simulations, astronomers infer halo profiles, concentrations, and even hints of triaxial shape. The debris is not random decoration, it is a dynamical measurement written in starlight. This method has a history. Early photographic plates revealed peculiar galaxies, and later, deep CCD imaging made faint tidal light impossible to ignore. With the rise of N-body simulations in the late 20th century, those strange shapes became understandable. Gravity alone could sculpt them. The famous antennae galaxies, for example, became more than a curiosity, because their tails could be reproduced by carefully chosen orbits and mass distributions. To understand outcomes, astronomers separate mergers by mass ratio. Major mergers involve comparable masses, often within about 3 to 1. In that regime, neither galaxy is a mere passenger, and both potentials are strongly perturbed. The encounter becomes a mutual transformation, with both disks losing their old order. Minor mergers involve a large primary and a much smaller satellite. They are more common and accumulate effects over long time spans. A single small accretion may seem subtle, yet a lifetime of them can steadily rewrite a galaxy's outskirts and thicken its disk. In hierarchical cosmology, this is the everyday background hum of growth, even when no spectacular tail is visible. A major merger can destroy a thin stellar disk. Violent relaxation scrambles stellar orbits into a spheroid supported by random motions. The term sounds dramatic, yet it describes a precise process. The gravitational potential changes rapidly, and stars exchange energy until the system settles. The relaxation is not about collisions, but about a collective redistribution of orbital energies in a time-varying field. In a disk, most stars share a preferred plane and direction. In a spheroid, stars move on many inclinations, and their collective motion becomes more like a swarm than a wheel. The galaxy's shape changes because the underlying orbital architecture changes. When that happens, the memory of spiral structure is not destroyed by impact, but by the loss of coherent rotation. The remnant often resembles an elliptical galaxy. Its light profile and kinematics reflect a history of energy redistribution during coalescence. Observationally, ellipticals show smoother isophotons, less ordered rotation, and stellar velocity dispersions that trace the depth of the final potential well. Some ellipticals also show subtle, boxy or disky shapes, which can hint at the merger's geometry and the amount of remaining gas. Yet the transformation is not guaranteed. If enough cold gas remains, dissipation can rebuild a rotating component after the chaos. Gas can radiate away heat, settle into a new plane, and form stars that re-establish a disk-like structure. In effect, the stars may be scrambled, but the gas can start over because it can cool and forget. This is one reason the same type of encounter can yield different outcomes. The gas fraction, the orbital geometry, and the timing of feedback all matter. Two mergers with similar masses can diverge because their internal conditions were not the same. Even the presence of a stabilizing bulge can change how strongly bars form and how efficiently gas is driven inward. Minor mergers usually do not erase the disk completely. They thicken it, heat stellar orbits, and build a more massive halo. The satellite stars are stripped first, and many end up in the host's outer regions, where the potential is weaker and mixing is slower. The disk survives, but it becomes dynamically warmer, meaning the stars wander farther above and below the midplane. Repeated minor accretions can create a thick disk and a stellar halo. They also deposit globular clusters and chemically distinct populations. Each accreted system brings its own star formation history, so the combined galaxy becomes a mosaic of ages and abundances. If we could tag every star by origin, the galaxy would look less like a single city and more like a continent assembled from many migrating pieces. This is hierarchical growth made visible. Big galaxies become big by eating smaller ones, even when the meal seems insignificant. The cosmic web supplies a steady stream of satellites, and gravity ensures that many eventually cross the point of no return. The question is not whether accretion happens, but how often it happens without leaving a glaring scar. The most dramatic fireworks come from gas. When galaxies interact, tidal torques remove angular momentum from the interstellar medium. Angular momentum is what keeps gas in orbit, so removing it is like loosening the grip that prevents collapse. Those torques can be amplified by bars and spiral distortions, which act like rotating levers inside the disk. Gas loses orbital support and flows inward. Central densities rise and star formation can spike into a short, intense starburst. In the densest regions, the star formation timescale can drop to tens of millions of years, which is brief by galactic standards. The inflow is often multi-stage, with gas piling up at resonances before plunging deeper toward the nucleus. Compression happens in shocks along tidal arms and bars. Colliding gas clouds cool efficiently, turning kinetic energy into dense molecular fuel. The cooling is powered by radiation in atomic and molecular lines, and the result is the rapid growth of cold star-forming clouds. In these compressed lanes, magnetic fields and turbulence also matter, because they can delay collapse until gravity finally wins. In visual terms, the disks become asymmetric and dust lanes sharpen into dark seams. Blue star clusters flare along distorted spiral arms, while the nucleus brightens behind veils of obscuring material. The galaxy looks like it is being pulled apart and lit from within. In narrowband views, glowing hydrogen can outline the shock fronts, tracing where gas is being squeezed into new stars. The starburst is often hidden from optical view. Dust absorbs ultraviolet light and re-radiates it in the infrared. What appears dim or reddened in visible wavelengths can be blazing in the far infrared, where warm dust reveals the true power output. This is one of astronomy's recurring lessons. What you see depends on the wavelength you choose. This is where luminous infrared galaxies appear. Lurgs and U-lurgs are frequently merger-driven systems with dust-enshrouded star formation. Their infrared luminosities can rival the total output of hundreds of billions of suns, concentrated into a compact region. Historically, infrared satellites made these objects impossible to ignore, because they show that some of the universe's brightest galaxies are bright in heat, not in visible light. Their luminosity is not just brightness. It is a measure of how fast gas is being converted into stars under extreme pressure. In these environments, the interstellar medium can be turbulent and dense, and the usual calm rules of star formation are pushed toward their limits. Star clusters form in crowded bursts, and the feedback from young stars begins almost immediately, trying to unmake what gravity has assembled. Starbursts also change chemical evolution. Supernovae enrich the gas rapidly, and winds can carry metals out into the circumgalactic medium. Elements like oxygen, silicon, and iron, made in stellar interiors and explosions, become traces of how a galaxy has lived and lost. The enrichment is fast enough that different regions can show different metallicities, revealing where gas flowed and where it was expelled. The circumgalactic medium becomes a ledger of past violence. It stores expelled material and regulates what can later cool back in. Some of that gas may remain hot for billions of years, while some may rain back as recycled accretion, fueling later episodes of star formation. When we observe absorption lines in background quasars, we're often reading this ledger indirectly, one pencil-thin sightline at a time. Feedback is the regulator that prevents runaway collapse. Massive stars inject energy through radiation pressure, winds, and supernova explosions. In plain terms, the very stars formed in the burst can push back on the gas that made them. The balance is delicate because too little feedback leads to overproduction of stars, while too much feedback can starve a galaxy for eons. In dense starbursts, overlapping supernovae can drive superbubbles. Those bubbles can break out of disks and launch large-scale outflows. When the hot interior finds a path of least resistance, it vents into the halo, carrying mass, momentum, and newly forged elements. In edge-on galaxies, these winds can appear as faint, biconical plumes, as if the galaxy is exhaling. Outflows remove gas and lower star formation efficiency. They also seed the CGM and nearby intergalactic medium with heavy elements. Over cosmic time, this process helps explain why even diffuse gas between galaxies contains traces of metals. It is a quiet form of cosmic pollution, and it tells us that galaxies do not keep their products to themselves. This connects to the missing baryons tension from earlier chapters. Some ordinary matter may be parked in hot, diffuse halos after repeated feedback. If baryons are heated and spread out, they become difficult to detect, and the inventory of matter becomes a problem of instrumentation as much as theory. The puzzle is not only where the matter is, but what temperature and density make it effectively invisible. Feedback is not only stellar. In massive galaxies, central black holes can add a second, stronger heating channel. Even before the black hole dominates the story, the merger's inflows are already preparing the fuel supply that can awaken it. The same torques that drive gas towards star formation can also drive it past the last stable orbits of ordinary galactic structure. Before we reach that engine, we need the question of morphology. The Hubble sequence looks like a taxonomy, but it can be read as a snapshot. When Edwin Hubble arranged galaxies by appearance, he did not claim an evolutionary path, yet later evidence made the sequence feel like a time-lapse frozen into categories. It is a reminder that classification can become interpretation, especially when time is too slow to watch directly. Spirals, lenticulars, and ellipticals are not fixed species. They are states shaped by gas supply, angular momentum, and environment. A spiral's arms are not rigid structures but patterns in a rotating disk. and that disk depends on continuing cold gas to remain thin and active. When that supply falters, the spiral can fade into a smoother, more lens-like lenticular form. Ellipticals are often red and dead because they lack cold gas. Their stars are old, and new star formation has been quenched. The red colour comes from long-lived lower-mass stars, while the short-lived blue stars have already burned out. In spectra, this aging shows up as weaker emission lines and stronger absorption features from mature stellar populations. Quenching can occur by gas exhaustion in a starburst. It can also occur when gas is heated or expelled faster than it can cool. Once the cold reservoir is gone, the galaxy may still contain plenty of baryons, but they are locked in hot phases that do not form stars easily. The galaxy can still glow, yet its future becomes quieter, because the raw material for new blue light is missing. In groups and clusters, the environment adds pressure. Stripping and starvation can remove or prevent replenishment of the cold gas reservoir. A galaxy moving through hot intracluster gas can lose its own gas through ram pressure, and it can also be cut off from the inflow that would otherwise refill it. Over time, this can turn a once blue spiral into a red system, not through a single catastrophe, but through sustained deprivation. In the field, internal processes can still quench. A deep potential can hold hot gas that cools slowly, limiting fresh fuel for a disk. In more massive halos, shocks can heat in falling gas to the virial temperature, and the cooling time can become longer than the time between disruptive events. The result is a galaxy surrounded by gas it cannot easily use, an ironic kind of abundance. Angular momentum is the hinge between disk survival and spheroid formation. Disks require ordered rotation and a continuing supply of cold gas. When rotation is coherent, stars and gas share a plane, and the galaxy can sustain spiral patterns and stable star formation. When that coherence is disrupted, the disk can thicken, warp, or dissolve into a more spheroidal distribution. During a merger, angular momentum can be transferred outward into tidal tails. The inner gas then collapses, feeding starbursts and bulges. The bulge grows not only by forming new stars, but also by rearranging existing ones into rounder, hotter orbits. In many galaxies, this bulge growth is visible as a brightening central concentration, even when the outer disk still looks recognizable. If the system later accretes high angular momentum gas, a disk can regrow. This is more likely when cosmic inflow continues along filaments. Regrowth is a kind of second chance, and it depends on whether the surrounding web still has material to deliver. It also depends on whether feedback and heating allow that gas to remain cold enough to settle, rather than hovering as a hot halo. Cold flows along the cosmic web can deliver fresh material. They can rebuild disks even after a major disturbance, especially at earlier epochs. In the young universe, gas fractions were higher, and inflow rates were larger, so rebuilding could happen faster and more frequently. This helps explain why we see many disturbed, clumpy galaxies at high redshift, yet still find rotating disks emerging from that chaos. This is why morphology is not destiny. A galaxy can be battered, then reassembled, if the universe keeps feeding it. The question becomes less about a single collision, and more about the balance between disruption and replenishment over billions of years. When we look at a galaxy's present shape, we're really looking at a temporary compromise between inflow, feedback, and gravity. Still, some mergers end the disk era. When gas is consumed, heated, or expelled, the remnant stays spheroidal and slowly reddens. Without new cold gas, the remaining star formation dwindles, and the galaxy's light shifts toward older stellar populations. The outer halo may still remember the violence in faint streams, but the inner galaxy becomes smoother, quieter, and harder to read. The tension between regrowth and quenching is the tension of galaxy evolution. It decides whether a galaxy remains a spiral or becomes an elliptical. It also raises a deeper question. How many times can a galaxy be rebuilt before its environment or its own feedback closes the door? And if rebuilding is possible, what subtle signatures tell us how many previous versions have already been erased? Now we bring the story home. The Milky Way looks calm, but its halo is full of evidence that it was built by accretion. From our position inside the disk, the sky hides the full structure, yet careful surveys reveal faint, coherent patterns around us. The challenge is partly geometric, because we are embedded in the very system we are trying to map. Stellar streams arc across the sky as disrupted satellites. They are the archaeological record of dwarf galaxies pulled apart by tides. Some streams wrap nearly all the way around the Milky Way, and others appear as shorter segments, like torn threads caught in the halo. In deep star counts, these threads emerge as subtle overdensities, barely above the background, yet dynamically unmistakable. As time passes, phase-space mixing blurs these structures. The stream's stars spread along the orbit, yet their shared motion remains detectable. Even when the stream becomes visually faint, it can remain dynamically distinct, and that distinction is a handle we can still grab. This is why kinematics matters so much, because motion can preserve what brightness loses. Gaia-like measurements turn this into a dynamical map. Positions and velocities reveal coherent groups that chemistry alone might not separate. Proper motions, parallaxes, and radial velocities combine into six-dimensional phase space, and that full information makes the halo readable in a new way. It is a shift from seeing the Milky Way as a picture to treating it as a dataset of orbits. Each stream carries a biography. Its orbit constrains the Milky Way's gravitational potential and the shape of its dark matter halo. If the halo is round, flattened, or triaxial, the stream's path and precession respond, and the stars trace that response faithfully. In this sense, streams are not only debris, they are test particles that let us weigh the galaxy from the inside. Streams also teach us about time. A narrow, well-defined stream suggests a relatively recent disruption, while a puffier structure hints at older accretion and more mixing. In this way, the halo becomes a layered record, with different debris corresponding to different epochs. The Milky Way's outskirts become a timeline, where the oldest events are the hardest to see, but not necessarily the hardest to infer. Some accreted systems were large enough to reshape the disk. Past mergers may have heated the Milky Way and contributed to its thick disk. The thick disk's stars tend to be older and have different chemical signatures, which fits a picture of early turbulence and repeated perturbations. Even without a single obvious smoking gun, the combined evidence suggests that the Milky Way's present thinness is an achievement, not a default state. The halo's metal-poor stars also preserve early enrichment. Their abundances connect back to first light and the first supernovae. When we measure ratios of elements in these stars, we are reading the yields of ancient explosions, preserved in stellar atmospheres like ink sealed under glass. These stars are time capsules because their surfaces change slowly and their chemistry can outlast the structures that once contained them. Our galaxy is therefore not an isolated island. It is a stitched-together remnant of many smaller galaxies, assembled over billions of years. The Milky Way's calm spiral arms are real, yet they float atop a deeper history of infall, disruption, and gradual construction. When we look up at the band of the Milky Way, we're seeing the present tense of a story written mostly in the past. That history is not finished. The local group's next major merger is already in motion, even if it feels impossibly distant. The future is written in measured velocities, and the numbers say the separation is shrinking. Even the quietest night sky contains a slow countdown, measured not in days, but in billions of years. Andromeda is approaching the Milky Way at over 100 kilometers per second. The collision is expected in roughly 4 to 5 billion years. The timescale is long enough that continents will drift and the sun will age. Yet in galactic terms, it is simply the next scheduled encounter. The approach is not a straight line because transverse motion matters, and small uncertainties still leave room for different choreographies. The first stage will be tidal distortion during the initial pass. Longtails and bridges will form as the disks are pulled and twisted. From a vantage far outside the local group, the pair would look like two luminous pinwheels reaching toward each other with faint streaming arms. The outermost gas and stars will respond first, because they are held least tightly, and their distortion will announce the encounter before the cores truly engage. As the galaxies swing past, their dark matter halos will overlap deeply. That overlap increases dynamical friction, which converts orbital energy into random motion in the surrounding matter. The orbit decays not because of contact, but because the moving masses raise gravitational wakes that drag them back. The process is subtle yet relentless, like a ship slowed by its own bow wave, except the ocean is made of dark matter. Gas dynamics will determine the fireworks. If enough cold gas remains, inflows may trigger starbursts in one or both galaxies. The central regions could brighten dramatically, while dust thickens and hides the most intense star formation from visible light eyes. In infrared, however, the remnant could glow with the signature of heated dust, revealing where the real energy is being released. yet the starburst likelihood is uncertain. Gas fractions will be lower than in the early universe, and feedback may limit the peak intensity. The Milky Way and Andromeda may arrive at the encounter already partially quenched, with less raw fuel to ignite the kind of infrared blaze seen in distant Ulurgs. Even so, modest bursts could still reshape the central regions, because a small fraction of a galaxy's gas can carry a large fraction of its star-forming potential. After the first pass, the galaxies will separate briefly. Dynamical friction will drain orbital energy, and the pair will fall back together. The separation is not an escape, but a recoil, and the second approach will be slower, deeper, and more binding. The sky, seen from within, would change over millions of years, with Andromeda swelling and stretching, then retreating, then returning with greater inevitability. The final coalescence will scramble stellar orbits. The remnant will likely be a more spheroidal system, sometimes called Milkomeda. Its outer halo will be a blended envelope of debris, and its inner regions will be dominated by stars on randomized trajectories. The central density may rise, and the old disks may survive only as faint kinematic memories embedded in a new structure. The Sun's fate is not a direct collision with another star. The probability of star-star impact remains negligible even in the merger. Space is still mostly empty, and the stars, though numerous, are separated by distances that keep direct impacts extraordinarily rare. The danger is not impact, but relocation, because gravity can rewrite the Sun's orbit without ever touching the Sun itself. The real change is orbital. The Sun could be flung outward, drawn inward, or left in a new halo-like path around the remnant. From a hypothetical viewpoint near Earth, the night sky would change slowly at first, then dramatically, as Andromeda grows larger and tidal distortions reshape both galaxies. The constellations would not merely drift, they would dissolve, because the background of nearby galaxies and star clouds would be reconfigured. Even these statements carry uncertainty. The outcome depends on the mass distribution, the gas content, and the details of the encounter geometry. Small differences in the transverse velocity or in the structure of the halos can shift the timing and the final configuration. This uncertainty is not a weakness, but a reminder that galaxy evolution is sensitive to initial conditions and that we are still measuring them. The scale is the point. A merger reshapes a galaxy without touching most individual stars, because gravity acts collectively over vast distances. The galaxy is not a solid object, it is a gravitational system, and the system can be transformed while its components remain physically untouched. That is one of the universe's strangest truths. Structure can be violent even when matter rarely makes contact. This chapter's violence is therefore a different kind of violence. It is the slow violence of orbits changing, gas collapsing, and structure rewriting itself. The drama is measured in kiloparsecs and gigayears, yet the physical processes are concrete. Shocks, torques, cooling, and heating. If we could speed the universe up, we would see galaxies flex like living things, constantly responding to forces that never sleep. We have followed collisions as engines of metamorphosis. They build bulges, thicken disks, grow halos, and sometimes shut galaxies down. They also leave behind faint signatures, tails and streams that act as the universe's forensic evidence, waiting for deep images and careful kinematics. Each faint arc in the outskirts is a question posed to us. What happened here? And how long ago did it happen? They also set up the next mystery. The same inflows that feed starbursts can feed the darkest engines at galactic centers. If gas can be driven inward past the scales where stars form, it can continue toward the nucleus, where an entirely different regime of gravity takes over. At that point, the story shifts from collective starlight to compact power, from sprawling structures to a pinprick of overwhelming influence. As gas funnels inward, it can awaken a supermassive black hole. The galaxy can light up as an active nucleus, visible across the universe. In that state, the core outshines the combined starlight of the host, and the merger's quiet talks become a beacon. The same event that makes tidal tails in the outskirts can, in the center, create a lighthouse bright enough to be seen across cosmic time. We transition from merging galaxies to accreting black holes. The dance of gravity becomes a blaze of quasars, and the stakes expand again. In the last chapter, gravity's dance drove gas inward and lit starbursts across merging galaxies. Now we follow that inflow farther, past star-forming clouds, toward a compact engine that can dominate an entire galaxy. camera leaves the glittering spiral arms and drifts toward the nucleus, where starlight thickens into a crowded glow. Dust lanes twist like smoke in a spotlight, and the motions become faster and less forgiving. On these inner scales, the galaxy's calm appearance can be misleading, because the deepest gravity well is also the hardest to see. The view tightens until individual star clusters blur into a luminous haze, and the center begins to feel less like scenery and more like a machine. At the centers of most large galaxies sits a supermassive black hole, hidden by definition yet revealed by motion. Stars and gas orbit as if around an unseen point mass, and their speeds rise sharply toward the nucleus. The closer an orbit gets, the more tightly gravity clamps down, and the more the velocity curve refuses to flatten. In the language of dynamics, the potential becomes centrally dominated, so the visible matter can no longer explain the observed accelerations. In the Milky Way, infrared tracking of stellar orbits around Sagittarius A shows Keplerian curves that demand a few million solar masses. Those stars are not vague smudges but individual points, traced night after night as they swing through pericenter. Some complete an orbit in only a couple of decades, and their trajectories close like clockwork around empty space. On screen, their paths can be drawn as nested ellipses, tightening into a tiny region where no luminous source sits. The logic is simple in plain terms. If something invisible can whip stars around that quickly, it must be both massive and compact. The mass is measured from the orbital period and size, while the compactness is inferred from how small the closest approach can be. No stable cluster of ordinary stars could hide there for long, because it would collide, evaporate, or shine. Even exotic alternatives struggle, because the required density would trigger rapid interactions and leave signatures we do not observe. In nearby galaxies, massive disks and ionized gas dynamics trace similar central masses, often millions to billions of suns. Water mixers, amplified microwave beacons in dense molecular gas, can map a thin disk with exquisite precision. When those matter spots outline a near-perfect rotation curve, they point to a central object with the density of a black hole. The measurements can be so sharp that we watch tiny clumps drift in velocity space, as though the galaxy were drawing its own blueprint. This is not a rare curiosity. The evidence accumulates across spirals, ellipticals, and lenticulars, and across environments from the field to rich clusters. When we weigh central regions carefully, the simplest explanation keeps returning. Most big galaxies host a black hole even when the nucleus looks quiet. The quiet ones matter, because they imply that activity is a phase, not a separate species. A dormant nucleus is not a different kind of object, only a starved one. Historically, the idea took time to settle. Early quasars, discovered as radio sources with star-like optical points, were so luminous that their distances seemed implausible. Once their redshifts were accepted as cosmological, the energy problem became unavoidable, and accretion onto a compact object rose as the cleanest solution. In the 1960s, the debate was not only about power, but about scale. How could something so small rival a galaxy's output? A black hole itself emits no light, so the story turns on what happens when it is fed. Gas drifting inward cannot fall straight in, because it carries angular momentum from the galaxy's rotation. Like water circling a drain, it spirals, and that spiral has to shed angular momentum before it can tighten. The inflow is therefore a problem of transport, not merely a problem of gravity, and galaxies solve it through turbulence, instabilities, and repeated torques. It settles into an accretion disk, where friction and turbulence convert ordered motion into heat. In modern terms, the disk's effective friction is largely magnetic, driven by the magneto-rotational instability that turns weak fields into strong turbulence. The gas rubs against itself through tangled fields, and the lost orbital energy reappears as radiation. In plain terms, the disk is a brake pad in orbit, and the braking glow is what we detect. The inner disk can reach temperatures of tens of thousands to millions of Kelvin, depending on black hole mass and accretion rate. For supermassive black holes, the peak often lands in ultraviolet, which our atmosphere blocks and dust readily absorbs. That hidden ultraviolet power is why an AGN can reshape its surroundings even when the optical view looks modest. If we could see an ultraviolet directly, many ordinary galactic centers would look startlingly intense. Accretion is efficient because the potential well is deep. Dropping matter near the event horizon can release a large fraction of its rest mass energy as radiation. Fusion in stars converts less than 1% of mass into energy, while accretion onto a spinning black hole can approach 10% or more. In the most favourable spin configurations, the efficiency can climb higher because the innermost stable orbit sits closer to the horizon. The difference is profound. Stars shine by slow nuclear bookkeeping, while disks shine by rapid gravitational conversion. A small amount of fuel can therefore outshine billions of stars. The comparison is almost unsettling. A region smaller than our solar system can radiate like a whole galaxy. That is why the nucleus can dominate the spectrum, bleaching the host into a faint halo of starlight. In images, the central point can saturate the detector, while spiral arms fade into a ghostly frame, yet the disk is not the whole engine. Above it sits a hot corona that scatters photons to higher energies, producing hard X-rays that pierce through moderate obscuration. The corona is likely a magnetized plasma, heated by reconnection events that resemble solar flares but on far more extreme scales. When ultraviolet photons from the disk collide with these energetic electrons, they are boosted into X-rays through inverse Compton scattering. Those X-rays can also reflect off the disk, imprinting spectral features that hint at the disk's inner edge and the black hole's spin. Around the disk and corona, dust and gas can form a thick, donut-like structure that blocks our view from some angles. This torus is not necessarily a smooth ring, but a clumpy, dynamic distribution of clouds. Each cloud can absorb and re-radiate, turning harsh ultraviolet light into warm infrared glow. In a visual sequence, the nucleus flickers behind drifting curtains, and the infrared view reveals what the optical view hides. The same object can look radically different depending on what the line of sight intersects. From one angle, we see straight into the bright core, and the spectrum is rich with broad lines and blue continuum. From another, the core is hidden, and we see only scattered light, narrow lines, and the thermal signature of heated dust. The physics is constant, but our vantage point edits the story. This is where active galactic nuclei enter as a family rather than a single type. A Seyfert galaxy shows a bright nucleus in an otherwise normal spiral, with strong emission lines from fast-moving gas. Those lines are fingerprints of ionized elements, and their widths reveal velocities of thousands of kilometers per second close to the black hole. The broadline region is small in size, yet it announces itself through Doppler broadening, as though speed were painted directly onto the spectrum. A radio galaxy appears dominated by enormous radio lobes, where jets deposit energy far outside the visible host. In deep images, the lobes can extend well beyond the starlight, like ghostly balloons in intergalactic space. Their radio emission is synchrotron radiation, produced when relativistic electrons spiral around magnetic field lines. The lobes can persist for tens of millions of years, so they become archaeological layers of past activity. A blazar looks violently variable and extremely bright because we are staring almost directly down a jet. The jet's radiation is beamed by relativity, so brightness is amplified and timescales shrink. A flare that might unfold over months in the jet's frame can appear as days, or even hours to us. That rapid variability is a clue to compactness, because only a small region can change so quickly without smearing the signal. The unification idea ties these categories together. Many differences can be explained by orientation, obscuration, and the presence or absence of powerful jets. If the broadline region is hidden behind the torus, we see only narrow lines and a dimmer optical core. If the jet is pointed at us, relativistic beaming amplifies the signal and compresses variability timescales. The model is not perfect, yet it gives us a disciplined way to translate appearance into structure. Unification is powerful because it turns taxonomy into geometry. It suggests that nature is not inventing separate engines for each label, but presenting one engine under different viewing conditions. It also hints at what we cannot see directly. Structures on light-day and light-year scales that are too small to resolve in most galaxies. The mind is forced to imagine a hidden architecture, inferred from spectra, timing, and polarization, rather than direct images. Quasars are the extreme end of this continuum. They are active nuclei so luminous that the host galaxy can become a faint backdrop. In visible light, the quasar can look like a single star, yet spectroscopy reveals its true distance and power. The word itself, quasi-stellar, captures that early confusion when the universe offered points of light that refused to behave like stars. Their spectra show broad emission lines from gas moving thousands of kilometers per second, and their redshifts place them deep in cosmic time. Those lines arise in dense clouds close to the disk, where intense radiation strips electrons and then allows them to recombine. Each transition emits at a characteristic wavelength, shifted by the expansion of the universe. In a single frame, we see both local violence and cosmological scale, bound together by the same photons. They function as beacons that let us probe the intergalactic medium, even while they complicate the story of early structure. A quasar's light is not just information about the quasar, but a long path through intervening gas. Along that path, the universe leaves a barcode of absorption features. Some lines mark diffuse hydrogen, while others trace metals that reveal where earlier generations of stars have already enriched the cosmos. The power source is still the same. A black hole does not need to be enormous to shine, but quasars often involve rapid accretion onto very massive holes. The luminosity approaches the Eddington limit, where radiation pressure balances gravity for ionized gas. At that limit, each photon's push on electrons can counteract the inward pull of mass. It is a natural equilibrium, and it turns light into a regulator rather than a mere byproduct. That limit becomes a natural speed cap on growth, unless the accretion flow bends the rules. If gas arrives in dense, optically thick streams, radiation can be trapped and advected inward rather than escaping. In such cases, the black hole may grow faster than the naive Eddington picture suggests, at least for a time. The question is not whether nature can do this, but how often it finds the narrow conditions to sustain it. Jets are the other signature that something compact is doing something violent. Many AGN launch narrow, relativistic outflows that remain collimated for thousands or even millions of light years. On screen, they appear as pencil-thin beams that terminate in bright hotspots, where the jet finally surrenders its momentum. The contrast is striking. An origin smaller than a planetary system, yet an influence that crosses intergalactic distances. The leading picture links jets to magnetic fields anchored in the disk and twisted by rotation. Magnetic field lines behave like elastic cords, and rotation winds them into helical structures that can fling plasma outward. In some models, the black hole's spin contributes energy through electromagnetic extraction near the horizon. The jet is then not just an outflow, but a circuit, with currents and fields shaping what matter can do. This is a subtle idea with a simple consequence. Rotation becomes fuel. If the space-time around the black hole is dragged by spin, magnetic fields can tap that rotational energy and channel it into a jet. The result is a cosmic accelerator that converts gravity and magnetism into directed power. Even without seeing the horizon, we can read the engines talk in the jet's persistence. Jets do not merely announce activity. They transport energy from sub-parsec scales to the circumgalactic medium and beyond, connecting the smallest and largest structures in a single causal chain. The jet's particles and fields carry momentum, heat, and turbulence into regions that would otherwise evolve slowly. In simulations, a narrow beam can trigger wide consequences, because the surrounding gas responds like a fluid under repeated punches. When jets slam into surrounding plasma, they inflate radio lobes and carve cavities in hot gas. In clusters, X-ray images show bubbles that match radio emission, implying that mechanical power is heating the intracluster medium. The cavities look like dark voids in X-rays, outlined by brighter rims where gas is compressed. Sometimes we also see weak shocks like ripples in a pond, spreading energy outward in concentric arcs. That heating matters because clusters should cool. Hot gas radiates in X-rays, and without an energy source it would lose pressure and flow inward as a cooling flow. Theoretical cooling rates once predicted torrents of cold gas and vigorous star formation in cluster cores. Observations instead show a gentler reality, with less cold gas than expected. The mismatch is a clue that something is repeatedly interrupting cooling before it can run away. Jets provide a maintenance mechanism, stirring and reheating the plasma so it cannot condense efficiently. The bubbles rise buoyantly, like hot air in a room, and as they rise they do work on the surrounding gas. Shock fronts and sound waves ripple outward, distributing energy in a way that can offset radiative losses. The cluster core becomes a place where gravity tries to settle the gas, while the nucleus keeps refusing to let it rest. This is feedback on the larger scales. A black hole smaller than the solar system can regulate gas across tens or hundreds of thousands of light years. The regulation is not gentle, and it is not always steady, but it can keep massive systems from turning all their baryons into stars. In that sense, the black hole acts less like a light bulb and more like a valve. The valve opens and closes in response to supply, and the whole galaxy feels the pressure change. The coevolution clue appears when we compare black holes to their hosts. Black hole mass correlates with bulge properties, including the stellar velocity dispersion in the central spheroid. The M-sigma relation is tight enough to suggest coupling, not coincidence. It implies that whatever grows the bulge and whatever grows the black hole are linked by shared fuel and shared regulation. We may be seeing an averaged history, where many chaotic episodes still converge on a common balance. Velocity dispersion is a measure of random stellar motions, a kind of temperature for the bulge's gravitational potential. A higher dispersion means a deeper well, and deeper wells tend to host more massive black holes. The correlation is not perfect, but its persistence across galaxy types is difficult to ignore. It invites a question that hangs in the air. How does a tiny central region know about the bulk properties of a much larger stellar system? Mergers from the previous chapter become part of this link. Interactions drive gas inward, building central starbursts and feeding the nucleus. Tidal torques can drain angular momentum from gas, and bars can funnel it further, step by step, into the inner few hundred parsecs. As the black hole brightens, it can return energy to the same gas that is trying to form stars. In a single merger, we can watch a galaxy feed its center, then recoil from the consequences. The galaxy is not only assembling, it is negotiating with its own center. The negotiation can be brief and violent, or slow and repetitive, depending on how much gas is available and how easily it can be destabilized. Every inflow is a proposal, and every outflow is a counteroffer. Feedback can take multiple forms. Radiative output can drive winds by pushing on electrons and dust, accelerating gas out of the nucleus. Dust is especially important because it couples strongly to light, so radiation pressure can shove dusty gas outward like a sail catching wind. Once gas is moving, shocks can heat it further and help it escape. The outflow can also sweep up surrounding material, turning a narrow launch into a wide galactic-scale wind. Broad absorption lines in some quasars reveal outflows moving thousands of kilometers per second. These features appear as deep troughs in ultraviolet spectra, where gas between us and the nucleus absorbs specific wavelengths. The depth and shape of the troughs imply massive, fast winds launched from near the disk. They are a reminder that spectra are not just chemistry, but kinematics written in shadow. On larger scales, ionized and molecular gas can be seen flowing out, carrying away the raw material for future star formation. Observations in optical emission lines trace warm ionized gas, while millimeter observations trace cold molecules like carbon monoxide. When both phases are outflowing, the message is clear. The impact reaches across temperatures and densities. The wind is not a single substance, but a multiphase storm. If enough gas is heated or expelled, star formation shuts down. The galaxy moves from blue and active to red and aging, because massive young stars stop being replenished. The color change is not instantaneous, but over hundreds of millions of years the bright blue population fades, leaving longer-lived red stars behind. In wide-field surveys, this shift populates the red sequence, a quiet lane of galaxies that seem to have ended their most creative era. In massive ellipticals, the black hole may enter a long maintenance phase, where low-level jet activity prevents the hot halo from cooling. The galaxy remains luminous in old starlight, yet its future becomes quiet. The nucleus can flicker, but even intermittent jets can keep the halo from tipping into a new cooling episode. The effect is subtle in optical light, yet dramatic in X-ray maps of the surrounding gas. This helps explain why the universe contains many red, dead giants. Stellar feedback alone struggles to keep gas hot in the deepest potentials. Supernovae inject energy, but in very massive halos the gas can radiate that energy away and remain bound. AGN feedback provides an extra lever, especially when the halo is massive enough to hold hot gas for billions of years. The deepest wells require the strongest regulators, and black holes are uniquely positioned to provide them. The black hole becomes a thermostat, keeping the system near the edge of cooling without letting it tip into a new starburst. The metaphor is imperfect, but the control loop is real. Cooling tries to feed the center, and the center responds by heating the reservoir. The loop is also delayed, which means it can overshoot, producing bursts and lulls rather than a perfectly steady equilibrium. Yet the story is not only suppression. In some environments, jets and shocks can compress gas and trigger star formation. Along jet paths, we sometimes find aligned star-forming regions. suggesting positive feedback under the right conditions. Compression can push gas over the threshold where gravity wins, allowing clouds to collapse and ignite new stars. The same shock that sterilizes one region can, in another, become the spark. The same engine can therefore create and destroy, depending on how its energy couples to the surrounding medium. A narrow jet might drill through diffuse gas with little effect, yet slam into a dense cloud and spark a burst of star formation. The outcome depends on geometry, density, and timing, variables that galaxies rarely hold constant. The mystery is not that feedback exists, but that it can wear opposite faces. This dual role deepens the central question of the series. How did galaxies form and evolve from the early universe to today, when their fates can hinge on an invisible object at the centre? The answer cannot be only about dark matter scaffolding or only about gas cooling. It must include the moments when a nucleus turns on and rewrites the rules for the entire system. If galaxies are ecosystems, then the nucleus is a keystone species, small in mass but large in consequence. To see these engines, we must use the full electromagnetic spectrum. X-rays reveal the hot corona and the innermost accretion flow, often even when dust hides the optical nucleus. In X-ray light, the sky becomes a map of compact power sources, and a galaxy's centre can suddenly outshine its own stars. Variability in X-rays also serves as a stopwatch, hinting at the size of the emitting region through light travel time. Infrared light reveals dust that has absorbed ultraviolet and optical radiation and re-emitted it as heat. On-screen cold galaxies become warm, and hidden nuclei glow like embers behind smoke. The infrared also traces star formation, so it forces us to separate stellar heating from AGN heating with careful diagnostics. In that separation lies a deeper question. How often are we mistaking a buried quasar for a mere starburst? Radio maps reveal jets and lobes, tracing mechanical feedback long after the brightest flare has faded. Radio interferometers can resolve fine structures, showing knots, bends, and hotspots that record the jet's interaction with its environment. Even when the accretion disk dims, the lobes can persist as a long-lived afterimage. In time-lapse, the radio sky would look like a slow choreography of expanding bubbles. Each band catches a different phase. A heavily obscured AGN may be faint in optical surveys yet bright in mid-infrared, where warm dust glows. A jet-dominated system may be radio loud even when the accretion disk is weak. A fading nucleus can leave behind radio bubbles as a memory of past power, while the optical core looks ordinary. The same galaxy can therefore change identity depending on which window we choose to look through. This multi-wavelength view also protects us from selection bias. If we only count optical quasars, we miss buried growth behind dust. If we only count radio galaxies, we overemphasize the jet-producing minority. The true history of black hole growth is stitched together from incomplete windows, each with its own blind spots. The task becomes an act of reconstruction, like inferring an animal from footprints in several different kinds of soil. The early universe raises the hardest version of this problem. We observe quasars at high redshift with black hole masses near 1 billion suns, when the universe was less than 1 billion years old. In visual terms, we are seeing a lighthouse already blazing when the cosmic shoreline is barely formed. The existence of these quasars forces us to ask how the first seeds formed and how fast they could feed. It also forces us to ask what their host galaxies looked like, and whether they were already mature or still assembling. Growing that large from ordinary stellar remnants is difficult under Eddington limited accretion, because the clock runs out quickly. The growth is exponential, with a characteristic E-folding time set by radiative efficiency and accretion rate. If the duty cycle drops, even briefly, the final mass falls short. The arithmetic is unforgiving, and it turns early black hole growth into a test of cosmic supply chains. One seed path begins with the deaths of massive stars, a population 3. A star can leave behind a black hole of tens to hundreds of solar masses, providing a small starting point. These first stars formed from pristine hydrogen and helium, and simulations suggest they could be unusually massive because cooling channels were limited. Their death seeded the early universe with compact remnants and the first heavy elements. In a sense, the first black holes were born alongside the first chemical complexity. If accretion stays near the Eddington rate almost continuously, repeated E-foldings can build a giant, but the duty cycle must be high. Any long interruptions make the math fail. That requirement leads to a practical question. Where does the fuel come from? And how does it keep arriving despite the radiation it triggers? The early universe was gas-rich, yet it was also fragile, because the first luminous objects could heat and disrupt their own reservoirs. Another seed path invokes direct collapse. In rare conditions, a pristine gas cloud might avoid fragmenting into stars and collapse into a massive black hole seed, perhaps 10,000 to 100,000 solar masses. Visually, this is a different birth. Not a star that dies, but a cloud that never becomes a normal stellar population at all. The collapse would be rapid, violent, and largely hidden, because the same dust-free gas that enables it can also trap radiation until the structure changes. That larger seed relaxes the growth requirement, but it demands special environments. It may require strong ultraviolet backgrounds that suppress molecular cooling, or dynamical inflows that keep gas hot and coherent. Without efficient cooling, the gas resists breaking into many small clumps, and a single central object can form. The rarity of such conditions may explain why the brightest early quasars are themselves rare, even if smaller black holes were common. There are also hybrid ideas. Dense star clusters can undergo runaway collisions, forming an intermediate mass black hole that later grows by accretion and mergers. Black holes can also merge during galaxy assembly, adding mass in discrete jumps. Each scenario must compete with feedback, because early accretion produces radiation that can blow away the very gas it needs. The early universe may have offered many routes forward, yet each route came with its own self-imposed obstacles. Even the mergers have a hidden complication. When two black holes coalesce, they can receive a gravitational wave recoil, a kick that can displace them from the center. If the kick is strong enough, it could delay growth by removing the black hole from its densest fuel supply. The early universe may have been a place where growth was both rapid and precarious. The same waves that carry energy away can also rearrange the future by moving the remnant off-center. These early quasars connect back to reionization from Chapter 4. Quasars emit hard ultraviolet photons that can ionize hydrogen and helium, but their number density at the highest redshifts appears limited. They may contribute locally, carving large ionized bubbles around themselves, while galaxies provide most of the photon budget. Still, even a minority population can shape the thermal history of the intergalactic medium. A single bright quasar can overheat its neighborhood, changing how later gas collapses. Quasars also act as probes of the young universe's gas. Their spectra show absorption from intervening hydrogen, including the Gunn-Peterson trough that signals a rising neutral fraction. In a single spectrum, we can watch the universe transition from transparent to opaque at specific wavelengths. The darkness is not emptiness, but neutral hydrogen swallowing the light. It is one of astronomy's most haunting inversions, where absence becomes evidence. Metal absorption lines reveal early enrichment in the circumgalactic and intergalactic medium, implying that winds and outflows spread heavy elements quickly. Carbon, oxygen, silicon, and iron appear as narrow features, each one a clue that stars lived and died before the quasar's light began its journey. The beacon is therefore both a light source and a backlight. When we read those lines, we are reading the aftermath of earlier generations, written into otherwise invisible gas. The feedback loop becomes the chapter's central tension. Galaxies funnel gas inward through bars, instabilities, and mergers, feeding both star formation and black hole growth. The black hole then returns energy through radiation, winds, and jets, altering the gas supply that made it luminous. The host and the engine evolve together, each shaping the other's boundary conditions. The same inflow that builds a bulge can also awaken the force that later limits bulge growth. We can frame this as a cycle of on and off. When cold gas is abundant, the nucleus can ignite and the galaxy can blaze, sometimes as a quasar visible across the observable universe. When feedback heats or expels the fuel, the nucleus dims and star formation declines. Over time, the galaxy's appearance becomes a record of how often this central switch has flipped. The record is imperfect, because dust, time, and distance erase details, yet the broad pattern remains. The switch is not perfectly periodic. It depends on stochastic fueling, on the geometry of inflow, and on the surrounding halo's ability to cool. It depends on environment, because clusters provide hot atmospheres that favour jet maintenance, while gas-rich groups favour bursts. It depends on cosmic epoch, because early galaxies had higher gas fractions and more frequent mergers. The universe changes the boundary conditions, and the nucleus responds in kind. This is why black holes matter to the fate of galaxies. They help set the high mass cutoff in star formation efficiency, preventing the most massive halos from becoming unrealistically bright. They help explain why bulges and black holes track each other across diverse populations. They provide a mechanism for rapid, luminous phases that we can see across most of cosmic history. They also provide a reason that two galaxies with similar mass can diverge if their central engines ignite at different times. They also remind us that the universe's most influential structures are not always the most visible. A black hole is an absence in space, yet it can dominate a galaxy's energy budget when fed. It can sculpt the circumgalactic medium, seed the intergalactic medium with heat, and alter the future of star formation far from the nucleus. The smaller scales can command the largest outcomes. The paradox is part of the fascination. Nothingness, given fuel, becomes governance. And so, a question lingers beneath every image of a bright nucleus and every map of a silent galaxy. How often does a typical galaxy experience these active phases, and how decisive is each episode in the long run? Are we watching rare catastrophes, or the normal heartbeat of galactic life? If the heartbeat is normal, then the quiet galaxies around us are not exceptions but pauses. We end with the unresolved edge of the story. We can measure black hole masses and map jets, yet we still debate how feedback couples to multi-phase gas in detail. We can see correlations like M, sigma, yet we still ask whether black holes regulate bulges or bulges regulate black holes. We can detect early quasars, yet we still do not know which seed path dominated, or how often nature found the required conditions. The uncertainty is not failure. It is a map of where the next discoveries will land. The journey to all galaxies is a journey through these hidden engines, because they turn galaxies into cosmic lanterns or extinguish them into quiet relics. But even black holes do not act alone. Their fuel supply and their impact are shaped by a larger scaffold that remains unseen. To understand why galaxies and black holes behave this way, we must confront the dominant ingredient shaping them all, dark matter, and the unseen gas surrounding galaxies. To understand why galaxies and black holes behave this way, we must confront the dominant ingredient shaping them all. The universe's visible light is a thin skin on a deeper gravitational body, and that mismatch is not metaphor. In this chapter, we enter the shadow realm where mass is mapped without being seen, and where the familiar sky becomes an accounting problem. On screen, the bright parts of a galaxy feel complete. A spiral disk glitters with young blue clusters, dust lanes cut dark calligraphy through the arms, and a warm central bulge glows like embers. Yet when astronomers measure motion, the light stops being a reliable guide. The stars behave as if they orbit inside something larger, heavier, and far more extended than the luminous disk. Galaxies look like islands of stars, yet their motions insist on hidden continents. In spiral disks, gas and stars orbit too fast to be held by starlight alone, especially in the outskirts where the stellar density thins. The classic expectation is simple. If most mass sits where most light sits, orbital speeds should decline with radius. That decline follows the same logic as planets around the Sun, where gravity weakens with distance and speeds fall. Instead, many rotation curves stay stubbornly flat well beyond the bright disk. Radio observations of neutral hydrogen at 21 centimeters trace gas far outside optical starlight, and the gas refuses to slow down. In the simplest reading, extra mass must be spread through an extended halo, dominating the outer gravitational potential. The halo's influence is not subtle. It often outweighs the visible galaxy by a factor of several. Historically, this was not a single surprising measurement that everyone immediately accepted. The pattern accumulated over decades, from early hints in galaxy clusters to increasingly precise rotation curves. Vera Rubin and collaborators helped make the case unavoidable by mapping optical rotation in many spirals, and the results repeated with unsettling consistency. The more carefully the outskirts were measured, the more the discrepancy hardened into a rule. This was not confined to one kind of galaxy, which is exactly why it mattered. Low-surface brightness galaxies amplify the discrepancy because their stars contribute little gravity, even in the inner regions. They look ghostly in visible light, like faint smudges against the sky, yet their rotation curves can be as high as those of brighter systems. If light traced mass, these galaxies should be fragile and slow, but they are not. Dwarf galaxies push the argument into an extreme regime. Their total starlight can be modest. sometimes comparable to a single large star cluster in a big spiral. Yet their internal motions, inferred from stellar velocities or gas dispersion, imply mass-to-light ratios that can reach tens or even hundreds. In plain terms, dwarfs behave like small lanterns hung inside large, invisible cages. Even in the Milky Way, the evidence is close enough to feel personal. Satellite galaxies orbit faster than the visible mass would allow, and their trajectories trace a gravitational field extending far beyond the disk. Stellar streams, ribbons of stars torn from disrupted companions, act like ink in water, outlining the shape of the galaxy's potential. Their bends, gaps, and precession patterns require a massive extended dark component. Clusters of galaxies deepen the case because their scales are larger and their dynamics are harsher. A rich cluster is not a quiet neighborhood but a collisionless swarm, where galaxies move at hundreds to over 1,000 kilometers per second. If the cluster's gravity came only from the visible galaxies, it would fly apart on a cosmic timescale. Instead, clusters remain bound, implying a deep gravitational well. The first quantitative hints go back to Fritz Zwicky in the 1930s, who studied the Coma cluster and found the galaxies moving too fast. His conclusion, missing mass, was initially treated as an oddity, partly because the data were limited and the idea was radical. Over time, better spectroscopy and larger samples confirmed that Zwicky's problem was not a fluke. Clusters were telling the same story as galaxies, only louder. Hot intracluster gas adds another layer, and it is visible in a way that galaxies are not. X-ray telescopes reveal a diffuse plasma filling the cluster, glowing through bremsstrahlung emission and bright-line features from heavy ions. This gas can outweigh the stars in all the cluster's galaxies combined, and its temperature, often tens of millions of Kelvin, reflects the cluster's gravitational depth. Yet even gas plus galaxies still fall short of the required mass. The cluster behaves like a gravitational well filled mostly with something collisionless and unseen. The word collisionless matters because it describes how the dominant component moves through itself. Galaxies pass each other without merging most of the time, and the inferred missing mass behaves similarly. It does not radiate away energy efficiently, so it does not collapse into a thin disk like baryonic matter does. Gravitational lensing turns this inference into a direct mass map. Here, the universe provides its own experiment, using background galaxies as test particles made of light. Strong lensing produces arcs and multiple images, sometimes even Einstein rings, whose geometry reveals the lensing mass distribution. The arcs look like smeared brushstrokes around a cluster, and their curvature is a measurement, not just a spectacle. Weak lensing is subtler, and it works statistically rather than dramatically. It measures tiny, coherent distortions in background galaxy shapes across wide fields, requiring careful calibration of the telescope's optics and the atmosphere's blurring. When thousands of faint galaxies are averaged, a sheer pattern emerges like a gentle tide in a sea of noise. Both methods weigh matter independent of light, and both reveal halos where starlight is faint. In clusters, lensing maps show mass peaks that do not always coincide with the brightest galaxies. Sometimes the mass follows the galaxy distribution, but sometimes it is offset, elongated or clumpy in ways that light alone would not predict. In merging clusters, the separation between hot gas and lensing mass becomes a crucial clue. The gas collides and slows, piling up into a bright X-ray shock front, while the dominant mass passes through with little drag. Visually, these mergers look like cosmic weather systems. X-ray images show bow shocks and cold fronts, like ripples in a hot ocean, while lensing reconstructions place invisible mass peaks ahead of the gas. This behavior matches collisionless dark matter more naturally than ordinary matter, and it challenges many purely gravitational alternatives. It is not that alternatives are impossible, but they must reproduce this specific separation without adding unseen mass. The cosmic microwave background adds a different constraint, written into the universe's earliest light. The CMB is a snapshot from about 380,000 years after the Big Bang, when electrons and protons first combined into neutral atoms and photons could travel freely. Before that moment, the universe was an opaque plasma, and sound waves, acoustic oscillations, rippled through it. Those ripples left a precise pattern of hot and cold spots across the sky. The CMB power spectrum encodes the matter content through acoustic peak heights and spacing. Baryons leave a distinct imprint because they add inertia to the photon, baryon fluid, boosting some peaks relative to others. Dark matter, by contrast, does not couple to radiation in the same way, so it shapes the gravitational wells without participating in the pressure waves. The best-fit cosmology demands far more matter than baryons alone can supply, and it demands that most matter be non-baryonic. This is where the story becomes less local and more universal. Rotation curves and clusters could, in principle, be blamed on complicated astrophysics or unusual environments. The CMB is different because it is an early universe measurement with a clean physical framework. When the same matter density is required both to fit the CMB peaks and to grow the cosmic web, the inference gains a rare kind of coherence. Large-scale structure formation ties the story together across time. Tiny CMB fluctuations grow into the cosmic web seen in redshift surveys, where galaxies trace filaments and walls around enormous voids. In three-dimensional maps, the universe resembles a nervous system, with bright nodes connected by faint strands. Those strands are not merely decorative, they are the scaffolding of gravitational growth. Baryons cannot clump early because radiation pressure resists collapse before recombination. Dark matter can begin forming potential wells earlier, letting structure grow fast enough to match today's web. Without dark matter, simulations struggle to build galaxies and clusters on the observed schedule, and the mismatch is not a small tuning issue. It is a timing problem written into the universe's growth history. So the evidence arrives as a web, not a single thread. Rotation curves, cluster dynamics, lensing, the CMB, and structure growth point to the same conclusion. Most gravitating matter does not emit, absorb, or scatter light in any ordinary way. The invisible majority is not a poetic phrase, but a measured accounting, one that keeps reappearing in independent ledgers. We then ask what this invisible structure looks like around a galaxy, because a halo is not just a number. In simulations of cold, collisionless matter, halos form with characteristic density profiles that emerge from hierarchical assembly. The density rises toward the center and falls gradually through extended outskirts, producing a steep inner region and a long fading tail. A Navarro, Frank, white-like profile is a conceptual anchor, not a perfect law for every system. In practice, the NFRW form summarizes a repeated outcome of gravitational collapse in an expanding universe. It reflects how matter piles up through mergers, accretion, and violent relaxation, which redistributes energies without requiring collisions. The central concentration depends on formation time, because earlier forming halos collapse when the universe was denser. That link between concentration and cosmic history turns halo profiles into a fossil record. Halo boundaries are defined by a practical threshold rather than a hard edge. The virial radius marks the region where the halo is roughly gravitationally relaxed, often defined by an overdensity criterion relative to the cosmic critical density. Inside it, orbits have mixed through repeated crossings and mergers, and the system behaves like a quasi-equilibrium structure. Outside it, matter is still infalling along filaments, not yet fully part of the settled system. The virial mass sets the depth of the potential well that baryons must climb or fall into. It also sets a characteristic virial temperature, which tells us whether infalling gas will shock heat and how long it will take to cool. In a Milky Way-sized halo, that temperature is of the order 1,000,000 Kelvin, hot enough to emit soft X-rays in principle. In cluster halos, it rises to tens of millions of Kelvin, making the intracluster medium bright and unavoidable. Halo mass shapes what kind of galaxy can exist, and it does so through several linked bottlenecks. Small halos struggle to hold gas against heating and feedback, limiting star formation and making them vulnerable to cosmic reionization. Intermediate halos can cool gas efficiently and build rotating disks, especially when angular momentum is preserved during accretion. Very massive halos shock heat in falling gas to high virial temperatures, making cooling slow and fueling intermittent growth. The visible galaxy is therefore a response to a dark scaffold filtered through gas physics. The scaffold sets the gravitational stage, but the actors, gas, stars, and black holes, improvise under feedback and cooling constraints. When we see a thin spiral disk, we are seeing baryons that manage to settle without losing too much angular momentum. When we see a quenched elliptical, we're often seeing a system where heating and mergers disrupted that settling. We also learn that halos are not smooth, even when the average profile looks simple. Subhalos survive as bound clumps within larger halos, remnants of hierarchical assembly that have not been fully shredded by tides. They are the expected homes of dwarf satellites and the seeds of future accretion. Their abundance and internal structure become tests of the dark matter model, because different particle properties change how easily small structures form. The Milky Way's satellite population is one local laboratory for this invisible architecture. Some satellites are bright enough to have been known for centuries, like the Magellanic Clouds, which hang in the southern sky like detached fragments of the galaxy. Others are ultra-faint, discovered only in the last 2 decades through digital surveys that can detect sparse star counts. Each new dwarf is not just a new object, but a new data point in the subhalo census. At this point, alternative gravity ideas enter the story carefully because the anomalies are real. Modified gravity models exist because they can reproduce some galaxy rotation curves with fewer free components, especially in regimes where accelerations are very low. In certain regimes, empirical relations between baryonic mass and rotation speed look tight and suggestive, as if the luminous matter knows the gravitational field. These successes force a serious question about whether gravity itself changes at low accelerations. The motivation is not contrarian but explanatory, and it has a history. When a pattern repeats across many galaxies, it is natural to ask whether the law is incomplete rather than the inventory. Modified Newtonian dynamics, for example, was proposed as a phenomenological adjustment that fits many disk galaxies with a characteristic acceleration scale. Even if one ultimately favours dark matter, the existence of such regularities is a clue that galaxy formation is not arbitrary. Yet the broader evidentiary web strains many modified gravity frameworks. Clusters still require additional unseen mass even when gravity is altered, because the discrepancy persists in the hot gas and the lensing signal. The CMB peak structure points to non-baryonic matter in the early universe, where modified gravity must reproduce a delicate acoustic pattern. Lensing maps in merging clusters show mass behaving differently from collisional baryonic gas, and that separation is hard to mimic with geometry alone. The simplest unified explanation across all scales remains a dark matter component plus general relativity. That does not mean every detail is solved, and it does not mean the dark matter model is beyond challenge. It means the same ingredient can be used to explain galaxy rotation, cluster binding, CMB anisotropies, and the growth of structure without changing the rules in different arenas. In science, that kind of cross-scale consistency carries weight. Even within the dark matter picture, tensions appear on small scales, where baryonic complexity is highest. Simulations of cold, collisionless matter often produce steep central density cusps, reflecting the natural outcome of collisionless collapse. Some observed dwarf and low-mass galaxies prefer flatter central cores, inferred from slowly rising inner rotation curves or stellar kinematics. This core, cusp problem may reflect baryonic processes that reshape the inner potential. Repeated bursts of star formation can drive gas outflows that fluctuate the gravitational field and heat dark matter orbits. The mechanism is subtle, but intuitive. If gas repeatedly piles up in the center and then is expelled by supernova energy, the potential well changes rapidly. Dark matter particles respond by moving to larger orbits, lowering the central density over time. In this view, the core is not a failure of dark matter, but a record of violent feedback. Another tension is the missing satellites problem, which is partly a prediction problem and partly a detection problem. Simulations predict many more small subhalos than the number of observed dwarf galaxies, especially around Milky Way-like hosts. Some subhalos may be dark because ionization and feedback prevent star formation, leaving them nearly invisible except through gravity. Observational limits also matter because ultra-faint dwarfs are hard to find against the foreground of Milky Way stars. The mismatch may shrink as surveys deepen, but it remains a key diagnostic. If the faint end of the satellite population continues to fill in, the problem becomes one of baryonic suppression rather than missing structure. If it does not, the particle physics of dark matter becomes more suspect, because it would imply fewer small halos exist. Either outcome teaches us something, which is why the census matters. Too big to fail adds a sharper edge, because it focuses on the most massive subhalos rather than the tiniest ones. The most massive predicted subhalos should host visible dwarfs, yet their inferred densities seem too high compared to observed satellites. The name captures the intuition. These halos are too deep to have failed at making stars, yet the corresponding galaxies are not seen. This could signal that baryonic feedback reduces central densities in the largest dwarfs. It could also reflect selection effects, tidal stripping, or uncertainties in mapping stellar motions to halo profiles. Dwarf galaxies are pressure-supported systems, and converting a velocity dispersion into a mass profile requires assumptions about orbital anisotropy. Tidal interactions with the Milky Way can also peel off outer dark matter, changing the relationship between present-day structure and original mass. Or it could hint that dark matter is not perfectly cold and collisionless. Possible particle-level solutions change how structure forms on small scales. Warm dark matter suppresses the formation of the smallest halos by erasing tiny fluctuations early because its particles have non-negligible thermal velocities. Self-interacting dark matter can redistribute energy in halo centers and create cores, because collisions among dark matter particles transfer heat inward. Each option must still match the CMB and large-scale structure, which strongly constrain departures from the cold paradigm. The small-scale problems become a pressure test, not a collapse of the framework. They ask whether the simplest model needs refinement, either through better baryonic physics or through new particle properties. They also remind us that galaxies are messy, and that the inner kiloparsec is a battlefield of feedback, turbulence, and star formation. When we interpret small-scale tensions, we are comparing an idealized simulation to a complicated reality. While the dark matter question dominates mass, a second invisibility problem haunts ordinary matter. Cosmology predicts a baryon fraction tied to the CMB and primordial nucleosynthesis, and that fraction is not negotiable without rewriting early universe physics. When we inventory stars and cold gas in galaxies, we find too few baryons, sometimes by a factor of 2 or more. The missing baryons are not missing from theory, but missing from our direct census. They are expected to exist in diffuse phases that are hard to detect, and the difficulty is physical. Diffuse gas can be so hot that most atoms are highly ionized, leaving few strong lines in the optical. It can be so tenuous that it emits almost no light, even if it fills enormous volumes. It can also be spread into filaments and halos, where surface brightness falls below the sky background, making it a challenge for imaging. The circumgalactic medium becomes the first hiding place. Around galaxies, beyond the bright disk, lies a vast reservoir of tenuous gas, extending to hundreds of thousands of light-years. It is multi-phase, spanning cool clouds, warm ionized gas, and hot plasma near the virial temperature. The CGM is not a decorative halo, but a working interface between galaxies and the cosmic web. It is both fuel tank and exhaust reservoir, and that dual role is central to galaxy evolution. Gas accreting from the intergalactic medium can enter the halo, cool, and eventually reach the disk where it can form stars. At the same time, feedback from supernovae and active galactic nuclei can drive winds that lift enriched material out of the disk into the halo. The CGM becomes a mixing chamber where pristine inflow and metal-rich outflow meet. We detect the CGM mostly in absorption, using background quasars as flashlights. A quasar is a beacon powered by a supermassive black hole, and its spectrum is a bright continuum punctuated by absorption lines. As quasar light passes through a galaxy's halo, specific ions absorb at characteristic wavelengths, leaving narrow fingerprints. Hydrogen Lyman alpha traces cooler and moderately ionized gas, while metals trace enriched outflows and recycled material. Different ions map different temperatures and densities, revealing a layered medium. OV often points to gas around a few 100,000 Kelvin, where oxygen is highly ionized, while Mejdudu can trace cooler, denser clumps. In the ultraviolet, these lines appear as delicate notches, and their Doppler shifts reveal velocities relative to the galaxy. The method is powerful but sparse because each quasar sightline is a narrow pencil through a complex volume. That sparseness is part of the mystery. A single sightline can detect a strong absorber, suggesting a dense cloud, while another sightline at a similar impact parameter sees almost nothing. This patchiness implies clumping, turbulence, and a range of cloud sizes, perhaps shaped by thermal instability and magnetic fields. It also raises a question that is still open. How long do cool clouds survive as they move through a hot halo? The CGM also appears in emission in special cases, especially in X-rays for massive halos. Hot gas around groups and clusters glows in X-ray lines and Bremsstrahlung continuum, and the brightness traces density squared, making the densest region stand out. Around Milky Way-like galaxies, the signal is faint and difficult to separate from foregrounds, including emission from our own galaxy. Yet the physics is clear because virial shocks and feedback can keep gas hot and extended. The problem is not plausibility, but detectability, and detectability shapes what we think we know. When emission is too faint, absorption becomes the main tool, but absorption requires bright background sources. That means our maps are incomplete by design, stitched together from chance alignments. As instruments improve, the CGM shifts from a theoretical reservoir to a measurable ecosystem. This gas matters because it regulates star formation efficiency, which is one of the deepest puzzles in galaxy formation. If galaxies contained and cooled all their baryons, they would make far more stars than observed, and the night sky would be brighter. Instead, star formation is inefficient across cosmic time, and most baryons never become stars at all. Feedback from supernovae and AGN heats and ejects gas, raising cooling times and lowering the fraction that reaches dense star-forming clouds. The CGM stores that displaced baryonic mass, sometimes for billions of years. In massive halos, gas can remain hot and quasi-static, supported by pressure and continuously stirred by minor mergers and outflows. In lower mass halos, gas can be blown out more easily, escaping into the intergalactic medium and reducing the baryon fraction inside the virial radius. Either way, the galaxy's visible mass becomes a small, processed fraction of what gravity originally gathered. Galaxy formation becomes a balance between inflows and outflows, and the balance is dynamic rather than steady. Filaments deliver fresh gas along the cosmic web, often with angular momentum that can build disks, and sometimes as cold streams that penetrate hot halos at high redshift. Feedback drives winds that remove gas from the disk and enrich the halo, and those winds can be multi-phase, carrying both hot plasma and cooler entrained clouds. Some expelled gas escapes into the intergalactic medium, and some falls back as recycled accretion. The galaxy's visible growth is the net result of this circulation, which means the galaxy is more like a breathing organism than a closed box. When star formation surges, outflows strengthen and the CGM becomes more enriched. When inflow dominates, the disk can rebuild and form new stars, often in rings or spiral arms where gas density rises. Over billions of years, the cycle writes a history into metallicity gradients and halo absorption patterns. The missing baryons likely extend beyond the CGM into the warm-hot intergalactic medium. Shocks from structure formation heat diffuse gas in filaments to 10^5 to 10^7 Kelvin, a range where hydrogen is almost fully ionized. At these temperatures, the gas is highly ionized and emits weakly, making it difficult to image directly. Instead, it is traced by ultraviolet and X-ray absorption from ions like Ovis, O7, and O-Phosphate. Each detection is a partial count toward the cosmic baryon budget, and the counting is painstaking. X-ray absorption lines are weak and require bright background sources, often active galactic nuclei, along with high-resolution spectrometers. Ultraviolet detections are more common, but they probe only part of the temperature range and can miss the hottest phase. The WIM is therefore a plausible reservoir that remains frustratingly hard to weigh. This is where the cosmic web becomes not only a map of galaxies, but a map of gas. Filaments are not empty corridors between nodes, but reservoirs of matter in a hard-to-see phase stretched across millions of light-years. The same gravitational collapse that builds halos also heats baryons into faint plasma, and the heating is a predictable consequence of infall and shocks. The missing baryons problem is therefore a problem of phase, not necessarily of location. The matter may be exactly where theory predicts, but hidden by temperature and density, which is a sobering thought. How much of the universe is effectively invisible simply because it is too thin to shine? How much of our cosmic inventory depends on the sensitivity of a detector, or the luck of a quasar alignment? The universe does not hide its matter maliciously. It hides it in plain physics. Lensing returns as a crucial census tool across these questions, because it bypasses the complexities of gas emission and star formation. By measuring halo masses independent of starlight, lensing reveals how much matter surrounds galaxies of different types. Galaxy lensing stacks many weak signals to infer average halo profiles and masses, turning small distortions into a statistical portrait. Cluster lensing maps show substructure and total mass, anchoring the high end of the halo mass function. These measurements connect the visible population to the underlying dark framework. They also allow a comparison between what a galaxy has in stars and what it has in total gravitating mass. When we compare lensing masses to stellar masses, the inefficiency becomes quantitative rather than rhetorical. Only a small fraction of available baryons end up locked in stars, and the peak efficiency occurs in a narrow halo mass range. Below that range, feedback and rayonization suppress star formation, leaving many halos dim or dark. Above it, virial heating and AGN maintenance keep gas hot and slow to cool, preventing the baryons from settling into cold star-forming clouds. The universe builds many halos, but it turns only some into bright galaxies, and it does so with a surprisingly selective efficiency curve. That curve is one of the most informative summaries of galaxy formation we have. The climax of the chapter is the paradox we cannot escape. We can map the invisible with exquisite precision using gravity's effects on light and motion, and we can do it across enormous distances. We can reconstruct halo shapes, concentrations, and growth histories statistically across cosmic time. Yet the particle nature of dark matter remains unknown, even though it dominates the mass budget. The dominant mass shaping every galaxy still refuses direct identification, and that refusal sharpens the mystery. The search spans from sky surveys to laboratories underground, because the question is both astronomical and microscopic. Telescopes can strain dark matter through structure, lensing, and cosmic history, effectively using the universe as a detector. Direct detection experiments look for rare collisions between dark matter particles and ordinary nuclei, often deep underground to reduce background noise. Colliders search for missing energy signatures that could indicate new particles, using conservation laws as a kind of trap. Indirect searches look for annihilation or decay products in gamma rays and cosmic rays, scanning the centers of galaxies and dwarf satellites where dark matter densities may be high. Each method probes a different coupling, and each has its own silence so far. That silence does not mean absence, but it raises the stakes. Dark matter could interact too weakly, or in channels we have not targeted, which would make it elusive by design. It could be a family of particles rather than a single species, with a richer dark sector that complicates expectations. It could be produced non-thermally, changing the usual relic density arguments that guide many searches. The universe has given us a gravitational fingerprint, but not a clear name. Meanwhile, the baryonic shadow world becomes more legible as instruments improve, and the improvements are tangible. Better ultraviolet spectroscopy expands the CGM census across galaxy types and environments, revealing how halo gas depends on mass and star formation activity. X-ray missions push toward detecting the faint whim in absorption and emission, aiming to turn hints into a budget. Fast radio bursts and their dispersion measures add a new handle on diffuse electrons along long sightlines, offering a complementary way to weigh ionized baryons. The inventory problem becomes a multi-messenger accounting exercise, and that is a striking change. A century ago, galaxies were island universes whose distances were debated, and the idea of weighing their halos would have seemed impossible. Today, we can stack lensing signals from millions of galaxies and infer average halo masses with percent-level precision. Yet we still struggle to see the baryons that should be there, and we still cannot catch the dark matter particle in a detector. We return to the central question of the series with sharper edges. How did galaxies form and evolve from the early universe to today, when most of their mass is invisible? The answer is that galaxies are not built only from what shines, even though light is what first caught our attention. They are built inside halos that set rotation, accretion, and merger rates, while baryons cycle through hard-to-see reservoirs. The visible galaxy is a temporary state of a much larger, darker system, and that perspective changes how we read the sky. A spiral arm becomes a pattern in a disk embedded in a halo, not a self-contained structure. A dwarf galaxy becomes a tracer of substructure, not merely a small collection of stars. Even a quiescent elliptical becomes a sign of a halo, where gas is kept hot and star formation is throttled. Now we bring the story home to a final tension. The universe is knowable in its patterns because gravity leaves measurable traces, and those traces can be modelled with increasing sophistication. Yet it remains mysterious in its causes because the dominant matter is still unidentified, and because much of the baryonic matter hides in diffuse phases. We can weigh halos, map filaments, and track missing baryons into hot reservoirs. We still cannot say what most of the universe is made of in particle terms, which is a remarkable gap for a mature science. What is the substance that holds galaxies together while refusing to shine? What is the full life cycle of baryons as they move from filaments to halos to disks and back again? And how much of galaxy evolution is written by gravity alone versus the messy details of feedback? With the universe mapped in both light and shadow, we turn to the farthest galaxies we can see. We ask what the total inventory implies for the universe's ultimate fate and for the limits of our journey. Deep fields stare at one tiny sky patch, and thousands of galaxies appear, specks and smudges that resolve into islands of stars. Long exposures stack photon upon photon, and infrared sensitivity pushes past dust into early epochs, where ultraviolet light has been stretched into redder bands. Their redshifts map time, revealing irregular star formers first, then calmer disks, then massive quenched ellipticals that have largely shut down. Cosmic star formation rises to cosmic noon at Z1 to 3, then declines as cold gas thins, halos heat, and feedback bites from supernova and growing black holes. Quenching follows two paths, through environment stripping in crowded regions or mass, and AGN heating in the biggest halos. Distances come from Type Ia supernovae and BAO rulers, fixing expansion history with two independent yardsticks. Acceleration implies dark energy and a horizon. So many galaxies are forever unreachable. The journey becomes observation, photons as messengers and telescopes as time machines. Locally, the Milky Way and Andromeda merge into a single remnant, while the wider sky reddens away until only nearby lights remain. Dark matter and dark energy remain unnamed, yet galaxies keep offering clues, each one an ecosystem of gas, stars, and gravity. We answer the opening question with humility, by learning to read what is slipping away. We set out thinking the night sky was a ceiling, then learned it is a map with no edge, drawn in delayed light. Redshift turned that light into a ruler and a clock, and multi-wavelength eyes, infrared through dust, radio through hydrogen, X-rays through hot plasma, let us read what ordinary sight cannot. Up close, the local group became our Rosetta Stone, where bars, spiral waves, streams, and a 4 million solar mass black hole revealed how galaxies recycle gas into stars and record their own collisions. Pulled farther back, the cosmic web appeared, a lattice of filaments and voids seeded in the CMB, where dark matter builds the scaffold and baryons merely paint it bright. Pushed farther still, deep fields in the first billion years showed galaxies as turbulent, clumpy, merger-fed experiments, lighting rionization in patchy bubbles, whose drivers we are still learning to name. Across cosmic time, collisions reshaped disks into spheroids, starbursts hid behind dust, and feedback, from supernovae and from accreting black holes, heated, expelled, or sometimes compressed the very gas that makes new stars. Yet two absences kept returning like a refrain, missing light and missing mass, and they taught us a method: infer the unseen through its fingerprints in motion, lensing, spectra, and statistics. Even the ordinary matter budget refuses to sit still, with missing baryons likely stretched thin through halos and the warm hot web, waiting for sharper ultraviolet and X-ray spectra and the dispersions of fast radio bursts. And over everything, accelerated expansion set a boundary we can measure but not cross, turning the observable universe into a shrinking archive as more galaxies slip beyond our horizon. Callback. So who built these cosmic cities? And what forces sculpted them from first light to now? And what do they reveal about our fate in the dark between galaxies? The answer is not a single architect, but a choreography. Gravity amplifying primordial ripples, dark matter shaping the stage, gas cooling and igniting, mergers rewriting forms, and black holes and winds enforcing limits, while dark energy quietly redraws the map of what can ever be reached. Final thought. To journey to all galaxies is to journey through time, because every photon is both a messenger and a delay, carrying a history that ends the moment we catch it. In their hidden structures, we find a universe that is knowable in its patterns and mysterious in its causes, and our place is to keep translating that light before the horizon edits the story. Call to action. If you want to travel farther than any ship can go, follow the next measurements: new infrared surveys, gravitational wave echoes, and deeper maps of the web, as they try to name the dark and complete the senses of everything. So who built these cosmic cities, and what forces sculpted them from first light to now? And what do they reveal about our fate in the dark between galaxies? The answer is not a single architect, but a choreography. Gravity amplifying primordial ripples, dark matter shaping the stage, gas cooling and igniting, mergers rewriting forms, and black holes and winds enforcing limits, while dark energy quietly redraws the map of what can ever be reached. To journey to all galaxies is to journey through time, because every photon is both a messenger and a delay, carrying a history that ends the moment we catch it. In their hidden structures, we find a universe that is knowable in its patterns and mysterious in its causes, and our place is to keep translating that light before the horizon edits the story. If you want to travel farther than any ship can go, follow the next measurements: new infrared surveys, gravitational wave echoes, and deeper maps of the web as they try to name the dark and complete the senses of everything.